Hi Ryan, how are you?
Hey Cecile, I'm doing well. Thanks for asking. Happy Friday. How are you? I need to step away for a few minutes here coming up, but it sounds like a great room, so thanks for leading.
Hello. Yeah, thanks. Yeah, we would like to welcome our guest, Professor Masoud Ataei.
Yeah, thanks everyone. Welcome Masoud specifically. Thanks for joining us as a guest speaker here. Yeah, so glad and honored to hear from you. So I may sound weird because I had a cold. So, but I'm very excited to learn from you today. And also, congratulations to your paper.
Happy Friday, everyone.
Hi Ryan, happy birthday, and hi Cecile, hi Hansen, hi everyone in the room. Welcome to the Quantum Photonics.
Yeah, hi Shara. Yeah, in the meantime, while we're waiting for Dr. Masoud to maybe adjust his sound and prepare his materials, may you tell us about our coming anniversary?
Yes, so we have a coming anniversary happening.
Are you going to pin a link at the top of the room, Masoud?
Yes.
Okay, that's great. Well, anyway, we're trying to invite more people in to come.
Yeah.
So,
please take your time.
Yeah, take your time too. In the meantime, I'm asking Shara to talk about our anniversary at the last week of April. So, Shara,
Congratulations.
yeah, we're 1 year in Clubhouse. I wasn't there, when they started. But anyway, we're finally 1 year here, and we hope that you can come during the time to also support us, to say hi. Yeah.
For sure.
Yeah. Okay, so for now, I give the mic to Shara.
Okay, thanks Daciel, thanks Masoud, and very honored to have you here. And thanks all the friends here as always. Yeah, we are approaching 1 year old with the Quantum Photonics Club. So yeah, we will have an anniversary week from the April 24th to the April 30th. So please, join our events if you have some free time. And we will also do the regular tech talk events that we are doing now here. And besides, we'll also have some music performance event, networking events. So please follow us, and you will see the schedule published handle time. Thanks, guys, for all your support for the past 1 year. It has been a wonderful journey.
Yeah, thanks, Shara. So maybe we will start shortly. Please let us know whenever you're ready, Dr. Masoud. Because I will start to introduce you. I would like to inform you that this session is being recorded. Well, if there is no objection from you, of course, and the replay can be heard anytime at the bottom of your profile Clubhouse, and that it will be at the profile of Quantum Photonics. So we can just reset the room later, and I will introduce you in 1 minute.
Yeah, sure. I'm ready.
Okay, that's great. So, we're very proud to have here our guest who will talk to us about Lemur Transform for Complex Data Analysis. He is lecturer at the University of Toronto, teaching machine learning and data mining, as well as the time series analysis courses. And he's an associate researcher at the York University, So such a short bio, but maybe you can see more of his bio in his profile. But of course, with a big accomplishment, and I would like to congratulate him for his recent lecture at the Fields Institute. And we are very lucky here that he is bringing his paper and his know-how in quantum photonics. So without further ado, I give the mic to Dr. Masoud Ataei.
I'm very glad to actually be here today, tonight. And I would like to thank all the audience to attending this talk. So this is really about a new transformation which I came across about 6 or 7 years ago when I was actually working on a rather different problem which is not really related to time series analysis. Back then I was working on the modified integer roundoff property conjecture, which is a conjecture which is a still open conjecture for the NP complete problem, which is the beam packing problem, and also it holds for the maximum cardinality beam packing problem, which is also known as the cutting stock problem. So this conjecture is pretty important because it's really beam packing problem was the first one for which the NP completeness was proven. So it is really an important problem, and I was just trying to at least tackle this conjecture from different angles, and during that time I just came across this idea that what would happen. The idea is that the problem is that we have a set of items, each of which have certain weight, and we have infinite number of bins, and let's say baskets, anything. We can consider them portfolios, each of them. And we would like to pack all these items, which each of them has a positive weight, and certainly we cannot pack items in bins so that they're going to exceed the capacity of the bin, and the capacity of all bins are identical. So the problem states that what is the minimum number of the bins that you need to use in order to pack all these items. The problem is a very difficult one, actually, to solve. And it's the oldest problem, as I mentioned, for which the NP completeness was proven. But during that time, I just realized that whether it's possible to somehow use some extended version of the averages. So instead of using the average to decide whether I can actually come up with some allocation scheme, would that be possible to just work with the entire range of statistics, meaning that starting from minimum of the items packed within each bin, minimum of course, the sizes or the weights, and this would extend to the case of the maximum, and within that you have the sample mean, which is known also as average, you have harmonic mean, you have geometric mean, contour harmonic mean, and interestingly enough, we can even write down the root mean square error in terms of combination of these means. But what is important is that whether this kind of continuity exists that can characterize the weights of the items within each of these bins that I'm dealing with. So this was the problem back in 2014 I was dealing with, and yes. That was a question?
No, please continue. I just came on stage.
Oh, okay.
Welcome, Serena. And yeah, I would like to tell those who just came in that you can see the paper of Dr. Masoud at the top of the room. So maybe please look at it at least on the first page. So Dr. Masoud, the mic back to you. Please continue.
Okay, thank you. So it turned out actually that idea worked pretty well, and it led to an algorithm which is actually one of the three algorithms developed to solve this NP-complete problem to optimality, meaning that it is possible to find the solutions to this NP-complete problem and prove that this solution is an optimal solution considering the conjecture of the MI-LUP is correct. So, of course, the method I used back then was branch and price method, but that is really just a prelude to just mention how I came across this transformation. So, what I used was the Lehman mean function. So, Lehman, whose name is also pronounced Lehman, and we have actually three of them, great mathematicians. But the one that I've always been fascinated by his works is the Derek Lehman, who was a number theorist, and the bit gaps in the prime numbers, that problem, that conjecture, or that's a very challenging part of the Riemann's hypothesis to deal with. That gap, studying those gaps, is really something that Lehman himself was interested in. So, if you take a look at the first page, you will see just a definition of this function, which we're going to also introduce it as an operator and consider it as just a transformation. I hope the notation is not going to be confusing. So, on page number 4, I will come back and mention different aspects of this transformation as opposed to the, as compared to the Fourier transformation or the Laplace transform, and why we even need like a new transform, because that would be a very, very important question to ask, that do we need at all to have another transform, because we already have at least 8 or 9 powerful ones. It turns out that the answer is positive when it comes to certain problems which give rise in area of the time series analysis, especially the time series analysis where we have the signals that have non-stationary behavior. Now, what this non-stationarity is defined, I will just gradually try to introduce you to all these concepts. So hopefully things are gonna make sense to some extent. But if you take a look at the function, which is defined as L of S, the relation is really a simple one. Well, what I have is a set of numbers, and these numbers are strictly positive. So I do have n positive numbers, and what I do is that I raise each of these numbers, which I these are going to be my observations in the signal, to the power of s. So s is my variable here. And then sum them up in the numerator. And in denominator, I'm going to just raise each of these observations to the power of s minus 1, and again sum them up. And this fraction is going to turn out to have interesting properties. I'm aware that maybe that notation of the s being equal to infinity and negative infinity might be a little bit confusing, but that is really one-point compactification of the R2. So I mean R. We can actually we can always do that, but what that really means is that okay, when s is really infinity, or let's say it approaches to infinity, what I'm going to obtain is the maximum of these positive numbers or the observations. Well, I always wish that the clubhouse had this whiteboard so one could write, because it's sometimes difficult to explain. But if one considers, for instance, s being equal to 1, then what's going to happen to the fraction? In the numerator, I'm going to have summation of xi's. And in denominator, I'm going to have summation of 1's. And 1 plus 1, and it repeats for n times. So it's going to be summation of xi's divided by sample size, which is the definition of the average. So for s being equal to 1, I would get the sample mean, or the average. What would happen if I plug in 0 for s? Well, in numerator, I'm going to get n, because it's going to be, all of them are going to be all the terms. All these summands are going to be 1, and I have n of them, so once summed up, I'm going to get n in numerator, and in denominator, I will get summation of xi's to the power of negative 1, which is really the reciprocal of each of these observations, and we don't have problem with this inverse because all the observations are strictly positive. So n divided by summation of 1 over xi's. And this coincides with the definition of the harmonic mean, which is very important mean known from the time of the Greeks. And another interesting case happens if I consider s to equal to half, 1 over 2. Well, if it is 1 over 2, and I only have 2 items, 2 observations, instead of having n observations, I would just restrict n to equal to 2. Then in numerator, I'm going to get summation of x1 to the power of 1 over 2, which is really square root of x1 plus square root of x2. And in denominator, I'm going to get a 1 over square root of x1 plus 1 over square root of x2. And once simplified, this would give me the definition of the geometric mean. So I'm pretty sure many of you actually remember the famous inequality among harmonic mean of a sample, the arithmetic mean, which is also known as the average of a sample mean, and the geometric mean. The inequality, which takes a lot of effort to kind of, not a lot, but quite an effort to prove in elementary probability course. Now here we can actually easily prove it by just showing that what we see here, the function, is monotonously increasing. So once I know it's increasing, then I'm going to be able to show that the harmonic mean is less than or equal to geometric mean, and that is less than or equal to arithmetic mean. Another important case is when s equals to 2. Well, when s equals to 2, in numerator I'm going to get the summation of squares of these observations, and in denominator I'm going to get just the summation of xi's. And this is again another important mean, which was also known to the Greek mathematicians, and they referred to it as contra-harmonic mean. So they were really fascinated by the harmonic series and also the harmonic mean itself, the contra-harmonic mean, and they saw somehow this relation between the average, the arithmetic mean, contra-harmonic mean, the harmonic mean itself, and soon we're going to see that these are really important means. But it is very interesting to also consider two other cases, the limiting behavior of this function. Well, what would happen if I take the limit of the fraction we see and let s approach infinity? Well, we know that when the exponent approaches to infinity, then in the summation of n terms, the one having largest base is going to dominate the entire series. So, and the largest one, of course, is going to be the maximum of the sample. So the numerator is going to actually be the maximum of the sample that I've observed as s approaches to infinity. So the maximum to the power of s, and denominator is going to be the maximum to the power of s minus 1, and once simplified I'm going to get maximum. So it means that the limit of the Lehman function as s approaches to infinity is going to be is going to approach to the maximum of the sample that I have. Well, that is very interesting property. But also we have its counterpart. When s approaches to negative infinity, it is not, of course it's expected that we're going to get the minimum, because, in the numerator, the dominating term is going to be the one which has, of course, smaller, the smallest magnitude at the base, and the same holds for the denominator, and once simplified, I'm going to end up with the minimum of my samples or observations. Okay, so in this case, it would make it much easier from a mathematical point of view if we consider the extended real line instead of the real line itself, and define our transformation, or the Lehman transform, in this as this fraction whenever the variable s falls within negative infinity to infinity, and we just define it to be the maximum of the sample when s equals to infinity, and minimum when s equals to negative infinity. Okay. wish I could actually share another picture. If you give me just 1 minute. So that's very helpful to build up the insight that what this function is doing. So we would see that it naturally gives us the distribution function based on which we can actually construct some unique cumulative distribution function, meaning that I can uniquely assign a random variable to that distribution function, and I'm using nothing but the observations without making any assumptions on the underlying distribution of the observations, without making any assumption whether they have been independently observed, whether the underlying distribution is identical for the entire random variables comprising the signal that I have. Without any assumptions, we're going to see that it is possible to actually construct in a very natural way the probability distribution functions just using the observations themselves. So this is a very interesting case and this is going to be non-parametric. Without requiring any parameters, we're going to be able to construct all these distributions. And what is important, since we are just on the same page, so if I take a derivative of my function L of s with respect to its variable s, and the variable s, I'm just going to call it sudency for a moment, and we will see that what we defined as a transformation is really a transformation that takes us from the time domain takes us from sudency domain to the time domain, and its inverse takes us from time domain to the sudency domain. Well, this is a very similar concept to the idea of the frequency, that we have Fourier transform that takes you from domain of frequency to the time domain, and its inverse takes you on the opposite direction from the time domain to the frequency domain. But what happens is that the nature of the sudency moments, I would call them, are different from the frequency. So almost all transformations we have in mathematics, they rely on the frequency domain. But this one is a purely statistical one. What it does, for any value of s, it gives me one of the statistics within the range from the minimum of the sample to the maximum of the sample. So for many of them, we don't even have name. And as a matter of fact, they are not even countable. And this is a great thing to have. It means that I can actually generate all the statistics. So in a case, this is really statistic generating function. So statistics is the science of studying the statistic, the plural form. So each of these values that we get when solving in the S is known as statistic. For instance, the sample mean is one statistic, harmonic mean is another statistic, and statistics is really generally referred to the science of studying each of, the family of these statistics. I would put the S at the end. Okay, so what I do have here, and I have defined as Lehman transform, it really is generating statistics for me for each value of S. let's take a look at its derivative, which is at the bottom of the page. And it reveals some interesting structure. So, the derivative is really going to be the function itself, or the transform itself, multiplied by the term that we see inside the bracket. But the difference is that the numerators are multiplied by the logs of each observation. And here log is the natural log, or we can call it ln. Well, this is quite interesting once we simplify it. On the far right hand side, we will see that the derivative can be expressed in terms of subtraction of observations, division of observations, or the ratio of observations, pairwise observations, and multiplication of pairwise observations. And of course we have both power operator and the log operator involved here. Well, I have deduction, I have division, I have multiplication, I have exponents, and I do have the log. So I can say I do have pretty much the important functions and the operators from algebra here. So this is really what to some extent is actually making, it's gonna account for the forthcoming results that we're gonna see, that how it's possible to really explain like very difficult phenomenon like the brain waves in terms of relatively simple transformation as compared to the case of the Fourier transform or the wavelet transforms. Okay. Okay, I would like you to switch to page, just scroll down to page number 6 on the PDF file. So this is a real signal. It's a signal observed from EEG, the electroencephalogram of some subject. And electroencephalogram, how it works is that the electrodes are placed on the skull, and they would record the surface electrical potential that exists. So it is really the potential that we see here is the potential of clusters of neurons altogether, and it is usually measured in microvolts. So it's very weak, and one needs to actually shape those regions of the skull that these electrodes are going to be put, and of course put some gel on it, and sometimes even they need to use invasive methods in order to get better measurements. But the EEG itself is non-invasive, and that makes it very important in the case of monitoring the patients, especially the patients suffering from psychiatric disorders, that they are put on different, let's say, antidepressants. But there are at least 50 different antidepressants. So the psychiatrist needs to plan over time and see whether this is responding to the medication. But there is no really quantitative method, to assess the improvement. This Lehman transformation is really going to provide us with the means to quantify certain aspects pertaining to the this specific disorder, which is the major depressive disorder. So the plot that we see here is a signal. So usually they would put either 19 or 64 or 128 electrodes on the skull, and they record the signal for a while, depending on the underlying disorder that one is interested to identify and study. For instance, for epilepsy, it would make sense to go for extended periods of time. However, for studying, the major depressive disorder, it would usually suffice to just record for 10 minutes, and these are extremely huge data sets. Even the 10 minutes, considering 256 hertz for the sampling rate, that is too much of data for 10 minutes. And let alone for like 24 hours, if one wants to record them, and on top of that, to analyze them. To analyze these signals, and considering that we don't have one signal, we're going to have more than one signal. We're going to have 64 signals, which are, of course, spatially related to each other. Not only throughout time, but also spatially, they are kind of correlated. So it is a very challenging task to perform, but for now, let's just focus on one of these signals and see what the Lehman transformation actually does. So on the horizontal axis, what I see is the sample. So samples, whenever they're time dependent, on the horizontal axis, one would usually put t to emphasize that the sequence that is observed has some temporal nature. But in general, it's possible to just put any index. And as a matter of fact, a time series is defined based on stochastic process. It's defined based on its underlying stochastic process. And what is a stochastic process? Stochastic process is the law based on which infinite number of trajectories over time could be observed, but once it is observed, we have only access to one of the realizations of these huge number of trajectories, potential trajectories which could have been observed. And time series data, which are also known as signals, these are just one of the realizations of all those trajectories. So it makes it very difficult to analyze such data, because this is not within the domain of the classical statistics. Since my observations now, they are ordered. There's a sequence here. And this sequence would render the central limit theorem, impractical. It's not possible to apply the central limit theorem to study such a time series unless one modifies it. And it would actually make most of the tools that we have from statistics almost useless, I would say, when it comes to studying these time series, because to begin with, they're dependent. There's a natural dependence and that dependence is really the order dependence. So it is this kind of problem, the time series analysis, is a very, very challenging one, and I will get back to that point again. But that signal that we see over there, if I apply the inverse of my transformation, meaning that on top, what I see is within the time domain. Now, what would happen if I convert it to the suddency domain, or the domain of the suddency moments? But an interesting thing is that, so around where we observe the maximum, we, by definition, it should just be positive infinity, and where we observe the minimum of the signal, it should just be negative infinity. So those top and the bottom lines, these are by convention, based on our definition, they should be negative infinity and infinity. But the rest of the signal, once it's converted into the suddency domain, it gives us another understanding of the signal. So what kind of understanding is that? If we pay attention, on the vertical axis, I've actually indicated 0. But 0 on the suddency domain, or S, if you recall, that would correspond to the harmonic mean of the sample. And the point 1, S being equal to 1, would correspond to the average, or the case of the S being equal to 2, which would go on top of the what we see as the point 0 that I've indicated there, that would correspond to contour harmonic mean. And all these values would fall within the red bands that we can see in the picture. Very well. What I see is a inverse transformation of the lemma applied to the sample. So it takes me to the domain of the suddency moments, and it really tells me that things are happening around the average, or within some band which is roughly starting from -2 to 2. And any value beyond this interval, from both sides, the positive and negative, they can be considered as anomalous observations to some extent. So we can use this potentially as a filter. For instance, the first anomalous one that I can observe is roughly at sample number, I would say 700, that I see there's very the peak is significantly outside of the region, the red region, the one indicated by the red bands. And the next one happens around the sample number 2000. So these two anomalous points, they do actually exist within the signal. But if one pays attention to the signal itself, it's hard to say that 2000 such anomaly exists. So what is this one is doing, the lemma transform, since I'm pretty sure our audience are familiar with some extent with the frequency domain analysis, is quite similar task, but from another perspective, from statistical perspective. The frequency domain analysis is based on decomposing the function into several functions having different frequencies. So these frequencies, these periodic functions that have different frequencies, can really tell me the nature of the time series that I'm dealing with. But it seems that there's also an alternative approach here. I can use this statistical transform to characterize my time series. But one application, one simple application could be for filtering, for detecting the outliers, or for so many other purposes. But what is important is really just the basic understanding of what the inverse of the transformation would do, and that would take us to this domain of the solvency moments. And I would like to see if there are any questions so far before moving on.
I can just briefly comment. I'm fascinated in where this is going, and I sort of scanned through the paper and the data that you're treating, and I'm frequently looking at, no pun intended, time series analysis where, yeah, sure, we take it into the frequency domain, but the window is always a challenge because there's often DC currents going through and over the time window, and this other complications. So I'm very interested in where the suddency domain and its inverse is going to handle the various frequency components over different time windows when those time windows aren't, or when the phenomena is changing. So I guess that's not a specific question, but certainly a comment at this point.
That's actually an excellent question. Excellent point actually you made here, because what happens is that this transformation, it has the homogeneity property of the linear transformations, meaning that if I multiply each of my observations by some constant c, then it's not difficult to see from the definition given at page 4 of the PDF file that the multiplier c is going to just raise to the power of s in numerator and raise to the power of s minus 1 in denominator. So once factored out, I'm going to end up with c multiplied by L of s. So this property is known as the homogeneity of the linear transformations. But the other property which would make a transformation or basically a function linear, that is not, that is certainly not true. I mean, if I consider if I consider the summations, if I add some constant to each of the observations xi's, then that doesn't necessarily mean that the L of s is going to equal to L of s plus c. So this is so for Fourier transform, we know that these two properties, they hold true, and many of the interesting properties that we see in the frequency domain, like how the convolution observed in the time domain gets converted to the multiplication in the frequency domain, or many other very interesting properties of the Fourier transform are really due to the linearity of the transform. But this Lehman transform, to begin with, is not linear, but it still has one of the conditions of the linearity. And another important point, because I want to really get back to what you mentioned, I find it extremely important, and it's really at the core of this this topic. Another property is that if I shuffle my sample, I'm going to get exactly the same value for a particular S. So it is order invariant, even though I am studying the time series. But it might sound a bit strange at first, that to know that we are going to treat time series, this transformation is treating the time series as if I can just consider any permutation of the samples, as if there is no order, whereas I define the time series to be a sequence, and a sequence naturally implies the order. So that would raise this question: how is it possible that a transformation having these two properties, the property of the scaling, which is also known as homogeneity, and the property of being order invariant in sample points, in observations, can actually solve the problem, which is the problem of well-ordered sequence. I mean, I do have a sequence.
So that's bizarre. So you can take this time series and say sort it by amplitude, and you're going to get the same 7C domain?
That's actually so you're asking about the relation between the frequency domain and the solvency domain, I believe. Is that true, sir?
Oh, I'm sorry, I talked on mute. The order invariance of the time series. You could...
Yes. Please go on.
So, yeah, I struggle to understand how you're capturing, the time-dependent phenomena.
I will explain it. And I am actually looking forward for the feedback from the audience, of course, to really get a better understanding of this transform. I see Ryan actually came on stage. I'll be glad to hear your feedback, Ryan.
Oh, hey, sorry, I just rejoined, so I'm catching up. But thanks for asking.
Okay, great. So I mentioned these two properties of the transform because these are really, as I mentioned, it is continuously continuous function, and the proof of the continuity is definitely not based on the epsilon delta definition of the continuity. It's going to require you to write down at least 10 pages of proof. It's a difficult function to deal with, even though it might look naive, but it is certainly a piece of work. But I really wanted to get to the point to mention what are the differences between this transformation and the other transformations in frequency domain, like the Fourier transform, and of course we know that Fourier transform has relation with Laplace transform. We know that they have relation with Mellin transform, and so on and so forth. All these transformations, they are somehow related, but there's also one very important transform in signal processing. They are known as wavelets. And what actually makes it kind of not possible to apply those transformations to study certain category of time series? Well, the answer lies within the concept of non-stationarity. So, we are allowed to apply Fourier transform for analysis applied to our time series. Either we can apply it to, let's say, the raw data, or in a much, I would say, elegant way, we can apply it to the autocorrelation function in the time domain to get the autocorrelogram in the frequency domain, based on which we can obtain, of course, the power spectrum and everything. But interestingly enough, we are allowed mathematically to apply this transformation as long as this property of stationarity is satisfied. And what is stationarity? Stationarity means that the mean of the process is going to remain constant as time goes by. So it's not time dependent. And the second condition would state that the variance of the stochastic process, whose realization we are studying here and calling it a time series, should be finite, because it is possible that it could be infinite, like the case of the Cauchy distribution. And the third one, which is a very important one, says that the autocovariance function defined on the time series, or equivalently we can talk about the autocorrelation function. The idea is really the same, borrowed from the correlation between two random variables. So once the covariance is normalized, divided by the standard deviation, it gives us a measure between -1 and 1, so we can have some very good interpretation of that. So on the time series, we have a very similar concept that measures the correlation between any pairwise points which are spaced, let's say, by some lag parameter h. Let's say there are two steps apart from one another. But the prefix auto here, it really means that this is applied to the time series. I mean that it traverses over all these time points and then finds the correlation, some kind of the overall correlation throughout the time series. Okay, depending on the value of the lag that I consider, lag meaning that how far apart two time points on the time series are located, I'm going to get different values for the autocorrelation function. But if this function is going to be only the function of parameter h, which we defined as lag parameter, only this distance between the points, and not the absolute value of the time point, then this would be the third condition for the stationarity once it's satisfied. So in other words, my autocorrelation function should not depend on the absolute location of the time points. Rather, it should depend on the difference between any time point, any two time points. So if that's the case, I can express my autocorrelation function in this way in terms of only the lag parameter. Then I can say that these three conditions, the constant mean, finite variance, and time-independent autocorrelation function, these would give me the one stationary time series. And this is usually known as the weak stationarity. Weak stationarity because we restrict ourselves to the L2 space, that we only consider the moments, the second moments. There's good reasons to do that, because most of the problems that we deal with from either nature or from any experiments, they are not going to satisfy the conditions of the so-called strong stationarity, which I'm not going to define it here, but strong stationarity briefly just says that I do know the underlying distribution, the underlying joint probability distribution, which is just referred to as the law generating all these observations. So that strong stationarity is a rare case to hold for time series, yet one of the very I would say famous sequences, time series that satisfies the properties of the strong stationarity is the white noise. The white noise process is strongly or strictly stationary. Now, without going into that direction, and let's just focus on this weak form of the stationarity, which only requires us to verify that the second moments are enough to characterize the time series. And the properties of the time series are not going to change throughout time. So I should not expect to see some rather bizarre behavior in my time series, as if I put it in front of mirror, I should see pretty much similar time series. I should not see something very different. So those familiar with the random walk would probably see this case. If we have a trend going upward, if I just put it in front of mirror, definitely the object that I'm going to observe is going to be different from the trend that I'm observing as a random walk. So random walk is a good case of the non-stationary time series. So the random walks, they are all non-stationary. We have simple random walk, or some random walk with drift, where a constant is added, or a random walk with drift term and the trend term. They are all non-stationary. Stochastic processes and of course their realizations are going to be non-stationary time series. But what happens in the case of the non-stationarity is that we do not have the mathematical framework. I mean, the necessary conditions are not just there to allow us to apply the Fourier transform in order to convert our time series from time domain, our observations from time domain to the frequency domain, or vice versa, if I apply the inverse of that. Okay. And the same holds for the wavelets. The wavelets, which are widely used to analyze the EEG signals, ECG signals, and they are really a it's just kind of localized Fourier series, we can say, but those also depend on this condition of stationarity. So we can use them as long as we have the conditions of the stationarity satisfied. But there are several ways that we can actually deal with this problem. Either we can convert our non-stationary time series into a stationary one, and then apply all those standard tools for analysis. Unfortunately, if the time series itself is a nonlinear one, there exists no transformation which can convert it into a linear time series. And by linear time series, I mean the one that can satisfy the properties of stationarity. So linear time series, there's this celebrated theorem known as the Wahl's decomposition theorem, which is formulated for the linear time series. The ones that any time series that I can convert it to a stationary one, there's a very nice theorem that telling me a lot about the properties of this time series, and perhaps the most important one would be the ergodicity of the time series, the stochastic process generating this. So the ergodic processes, these are very important ones if the conditions hold true. Regardless, I'm looking at another situation here, that it is not even possible to convert the time series into stationary one. So in that case, I do not have I would say enough rights from a mathematical perspective to just simply apply my very useful Fourier transform and study this signal in the frequency domain. And when one looks in the papers using wavelets for analysis of, let's say, EEG signals, it is quite, to some extent, it's quite obvious that the methods are really convoluted. They're very complex to the point that sometimes it's really not possible even to understand what's going on. It's just too many pieces put together to make this analytic framework working. And how it's working, it would be the interpretation is going to be very, very difficult. So I would say the first advantage of the Lehman transform, the solvency domain that you mentioned, because it apparently doesn't really care about the order. It doesn't care about the cycles that might exist. It is just taking another approach. It's looking at the time series from a completely different perspective, and it can be applied to both signals or time series data as well as the data which are not ordered. This is another interesting property because it's basically order invariant. So I can also apply it to any arbitrary collection of observations. And most importantly, perhaps, is that I can consider the random variables sitting instead of the observations. In that case, I can find distributions, but in a different way than it's usually we're familiar with from statistical courses, in a way that I would just determine my solvency moment And if I'm interested to see what's happening within the neighborhood of that suddency, let's say the average, I would just consider S to be equal to 1 and perhaps write down the Lagrange-Berman series around that point. So it's very similar to the idea of the power series. And that would give me the behavior of the sample mean. So how I'm characterizing these statistics is really by taking advantage of very nice properties of the suddency moments. So one of them is it enables me to do the filtering task, which is a very important task in signal processing. Often what happens in analysis of EEG signals is that if one blinks, then the signal is going to just get some very, I would say, strange values. Like instead of the signal, usually the neurons, the lowest signal, the lowest electrical potential that they can reach is negative 70 microvolt. And once they are fired, this neuron fires, it will reach to positive 35 microvolt, and then it will just come back to the resting state until the next firing happens. But if the person whose EEG signal is being recorded only blinks, then the behavior of the signal is you're going to see very exotic behavior in the signal. So usually to overcome these problems, there's always a well-trained operator who will spend hours removing the artifacts from the signal, from the EEG signal. Very well. This is necessary, of course, for the case of applying any frequency domain analysis tool. But when it comes to Lehman transform is a statistical one, and one of the statistical properties that we have for different statistics is their robustness. So robustness towards, let's say, outliers, or robustness towards certain, with respect to other criteria that we can consider. So we do not need to actually perform this pre-processing task of removing the artifacts. And this step itself is very important in signal processing because it is done in a purely subjective way. I mean, if one gives me the same raw data, I might just come up with not completely different, but I would say definitely different refined signal where the artifacts are removed. So there's no need to actually filter the noise in the Lehman transform because it already takes care of the noise due to the very fact that it is defined as a statistical transform. Now, the second interesting case is that, as I mentioned, when wavelets are used, or even any tool from the frequency domain analysis, I've noticed over time that, having a very profound understanding of the frequency itself, and of course anything related to this domain of the frequency, it takes time, and it requires certain, I would say, certain preparations, certain steps for preparation, and it is usually not easy to interpret, at least for those who are not within are not specializing within the areas like mathematics or theoretical statistics, it would actually pose quite challenges to make interpretation. Of course, it happens that once like psychiatrists, they are all familiar with the alpha waves, they are familiar with the beta waves, the gamma waves, but what they really mean, the insight behind these waves and what is going on the frequency domain analysis, it seems that there is this kind of I would say it is the lack of interpretability of the frequency domain tools that make it sometimes difficult for those who are not specializing in these fields to apply the tools. And those are the end users. I mean, psychiatrists, at least in this work, neuroscientists, and I actually come from the financial background, so I've also applied this transform, of course, to the financial time series. But again, over there, when it comes to analyzing the time series in the frequency domain, we have the same kind of interpretability problem because, yeah, of course, seeing things as decomposition of waves is very useful, but what if I'm not even able to apply the Fourier transform? So what can I say for such thing? So in case of even applying, there's this lack of interpretability, but as you hopefully, hopefully I was actually able to show that with just these statistics are more tangible as compared to the frequency itself. I mean, the concepts. I mean, we are all familiar with the maximum of the sample, with the minimum of the sample, with the average of the sample. But if I ask one, okay, how would a frequency of 1 Hertz differ from, the plot generated by frequency 1 would differ from 1.2, it would require that person to really think for a few seconds at least. But for the statistics, that's not going to happen. At least we are familiar with many of them. And I'm just suggesting that, okay, let's just consider this spectrum of statistics instead of considering very few of them. So it is, I would say, it is, in a sense, more interpretable when we work within the sub-MC domain instead as compared to the frequency domain. Another interesting point is that, as I mentioned earlier, this transformation doesn't really care about any kind of dependence that might exist among my observations. I mean, I never require the IID assumption on the underlying random variables comprising the stochastic process in order to be able to characterize my time series. Why is that so? Well, yes.
Hey, Masoud. Sorry, I finished driving not long ago, so I think I might have missed a good part of it. So I have a question. Just from the formalism, I must have missed something. Seems that it's invariant to the ordering of the data. Is that correct?
It is. It is.
So when you say the inverse transformation, you mean a class of functions that basically that's a quotient that you have an equivalence relationship over the order. Is that correct?
Well, that would be correct in our general case, but what happens is that if only out of these n observations, if I only have one of the observations, its value, differing from the rest of the observations, then I do have the strict monotonously increasing function. So I can define the inverse of the transformation.
You mean if you have only one sample, xi, that's different in the whole series? Yeah, okay, I understand. But if you permute the ordering, then you get the same transform, right?
I do get the same transform.
Okay. And another question, that if you translate the sequence up and down, would you get different?
Unfortunately, yeah, that's what I mentioned. Out of two conditions for linearity, only the second one, the scaling or the homogeneity, that holds.
Right. Okay. And then you have to, I suppose, when you process the data, you have to move up to the positive quadrant.
Yes. But it's not going to be any transformation. I'm going to actually cover that we are going to use, I would say, normalization based on the Lambert W function, because those transformations, they preserve the structure of the data. So rescaling, rescaling between 0 and 1, it will actually, it's a very interesting point. I wish I had the plot here. So let's say I rescale all my data to the interval from 0 to 1. And I would consider the interval to be open on the left end, so not including 0. Then something interesting actually happens if you pay attention. The function is monotonically increasing, and it has actually at least one inflection point, and that inflection point is going to be different from the sample mean, the average.
So sorry, when you say the function, are you talking about the transform?
Yes.
Function
I mean
the S.
Yeah, I mean the transform, but just to make it relatively easier for at least some of the audience to follow, I'm referring only to the functional form that we see, the summation of x raised to the power of s divided by the summation of the x raised to the power of s minus 1. Only the middle part, considering that part.
Got you. And yeah, so you're saying that the function is monotonically increasing, and then starting from 0, monotonically increasing, and then you have an inflection point. Maybe is it like convex to the left of the inflection point, and
it is actually it is as s approaches to negative infinity, it's gonna become convex. As s goes to positive infinity, it will become concave. But there was a proof. This is an area that we don't find actually much of work done. There was a proof presented around I guess 2013, showing that the function, the Lehman mean function, which is the one we see inside, I mean the second term, the fraction, that would be short convex function. But later on, it was proven wrong that such a property doesn't hold always, and it is still a very challenging task to even say whether this is at least short convex function or not. But certainly on the left tail we have the convexity, and on the right tail we have the concavity. So there's at least one inflection point. The graph really looks like the graph of the logistic function. In this case that we have, it's very similar. It doesn't necessarily going to coincide. In the case that we have normalized or scaled all our observations within the interval from 0 to 1, the plot is going to look like the plot of the logistic function.
Yeah, that's reasonable, because you have going from minimum to maximum, and then you have all the kind of averages in between that you have inequalities between, let's say, arithmetic average and geometric average and all sorts of other kind of weighted averages, and then I suppose that they all kind of keep the monotonicity between them, right?
Yes, exactly. So when that happens, then this reminds of distribution functions, right? Because any distribution function has to satisfy three properties. It has to be right continuous, which in this case, I mentioned actually the proof of continuity is like a 10-page proof, because we cannot apply the epsilon delta definition. But anyways, it's a continuous function, and definitely so it's right continuous. The other proper condition says that the limit of the variable, the limit of the function as the variable approaches to positive infinity, should equal to 1, which is the case here. And for the case that s approaches negative infinity, it should equal to 0. So any function satisfying these three properties, it is referred to as a distribution function. Now,
you mean cumulative distribution function, right?
Not necessarily. It is just a distribution function.
I thought you have to approach 1 to
yes.
Was it approaches positive infinity, and then some
yes.
monotonic? Is that right?
Yes. Now, from looking from measure theoretic point of view, this is generally referred to as distribution function without even considering it like assigning any measure to it. Okay, assigning a random variable to it. But what happens is that if I use the theorem, which is known as the theory extension theorem, that asserts that there exists a unique Lebesgue-Stieltjes measure which is associated to this particular distribution function. In that case, I can define a real valued random variable s, uppercase S, which takes its values in the support of the R, and that could be considered as the cumulative probability distribution function, or the CDF of my random variable. And this CDF is going to coincide with the distribution function. So whenever we are able to construct distribution function, we can always assign a random variable to it, a unique random variable, and consider that distribution function as the cumulative distribution function of that random variable.
But yeah, sure. That's. But how do you apply that to the analysis? If or is it just a cute, nice theorem, a nice property?
Yes. So what I'm doing is that it's very interesting. Without using any parametric form considering any parametric form, or not even using the non-parametric statistics, I'm just constructing this probability distribution functions using the data themselves, as if the observations are my parameters. You see the point here?
Yeah, I guess what I can see is, let's say if you consider these previous time series, a set of samples, right? And then you convert it into a suddency, right? That's what you call it.
Yes.
Suddency domain, and then you get another distribution random variable, and you can basically match them up. Yeah, but then what? I mean, it's definitely a nice property, but then what?
Okay, what happens is that I'm defining a probability distribution function on the domain of suddencies, and that is what is the interpretation of that? Well, that would tell me, if we take first, it's differentiable, yeah? It is definitely differentiable, and it is absolutely continuous. So once we differentiate, we get the density function. And the density function is going to be, depending on the data I've observed, it can be unimodal, it can be bimodal, it can be trimodal, it can get so many different, there are so many variations. But what is happening is that what it means is that this distribution, this density function, tells me what is the probability that average sample mean is the dominant statistic within all range statistics, which are of course not countable, even not countable.
Yeah. No, okay, great.
Okay, so I just with this example of the logistic type, it looks really like a logistic function. I just created a distribution function, well, without requiring any form for the distribution. It is only dependent on the sample points. If I make another observations, I'm going to get different observation. So
yeah, I think it's very nice. Now, the only thing is, it's the ordering, the invariance with respect to the ordering is kind of a little bit concerned, because the time series is supposed to be dependent on time, and you order the samples by time. Now basically the time has gone.
Yes.
So it seems like you have a sample that's irrespective of time, and seems like certainly yes, I do agree that you can get all the sample statistics, but the time is gone. So it seems like
what happens here. At least I'm just sharing my understanding, because there's obviously many angles that I'm not capable of realizing this for. But there's certain things, out of two conditions of the linearity, we do not have the first one satisfied. The one that makes like the Fourier transform to
the translation, right? You're talking about.
Yes, we do not have that satisfied. So we only have the second one, the scaling or the homogeneity satisfied. So apparently, when those two are satisfied, then we are familiar with the behavior of the transformations, like the Fourier transform. What it does, it converts the convolution on the time domain to multiplication on the frequency domain. But it seems that this order invariance property and the homogeneity property or the scaling property, these two together, they are capable of capturing all the nonlinearity that exists within that time series, because I'm studying the non-stationary time series. The time series that I'm not even capable of applying the Fourier transform.
Yeah, but the thing is, because the stationarity is basically if it's a property that the moments are independent of time, but we're from the outside has dropped the time, has already gotten rid of time. Sure, it doesn't depend on time. So, I mean, it seems that by definition, it's not time dependent, right? So I'm just wondering whether, the if you do need to deal with time, then I guess do you have to do something else?
Okay, what happens is that, and this is this is the aspect it is still unclear to me, but what is really because I'm going to show you. I know that you're a big fan of the number theory. I'm going to show you how how these transformation is going to look like on the complex domain, and it's going to be a little bit surprising to see that. But before that, what happens is my understanding, at least, after all these years, my understanding is that this time invariance is really telling me that together with the scaling, it's somehow it is dealing with the nonlinearity which no transformation is capable of actually converting it to a linear time series. So it doesn't, in order to convert a non-stationary time series into a stationary one, if it is convertible, then I can always find a transformation or a composition of transformations which will eventually convert that non-stationarity into a stationary time series. But if a time series itself is nonlinear, the dynamics that are generating that behind that time series are just more complicated. That then it is impossible to find any transformation which can be applied to the nonlinear time series and convert it to a linear one, the one that stationarity is going to hold true. Okay, in that case, it is somehow my understanding that this reordering of the sample points, the observations within the time series, and here we are really, it's the abuse of language, I guess, to say that we have a sequence, but still we are permuting the the members of this sequence, the observations. This permutation or the reorderings, together with the scaling, enables the lemma transform to capture the nonlinearity existing within the time series, and then deals with that nonlinearity in a domain, but it is the domain of statistics. Why is that important? Because here I'm not going to describe the behavior of my time series in terms of periodic functions, decomposition of a function into several functions. I'm rather going to characterize its behavior based on uncountable number of statistics, as a matter of all the statistics. Because once I have the range statistics, I can also just translate them. I can get different kinds of all kinds of statistics. Once I have the ones from minimum to maximum, they are referred to as range statistics. So it is really, this is the essence of the transformation, but there are obviously aspects to this transformation that are unclear to me. I would actually be glad to hear your feedback, and of course feedback from the audience would be much appreciated on this.
Yeah, so I think I'll talk about the nonlinearity a bit later. So it just came to me that when you were talking about the transform, one second. Sorry about that. So basically, if we now I just thinking about the mathematical property of it. So we do the transform if you have a finite number of them, finite number of samples, and then you do the transform. The domain of S is the whole real axis, right? I suppose I can also extend it to the complex plane, and then I would think that you will get kind of a analytic function, right? The a more meromorphic function, and then also these are so would say that these are not S the function. So then these are not completely like the degree of freedom is probably in the equivalent to the S. The number or even countable samples. Well, actually, yeah. Well, I mean, if we talk about countable samples, then we have to talk about the convergence and all that stuff. But let's say a finite number of them. So I suppose that you would have any compact set. The value of any compact set would determine the rest of the value on the complex plane or the axis.
Yeah. Okay. I do have the plots. If you give me 1 minute to just upload them, it might be actually helpful to look at the plots and then continue discussion.
I could just say it's an interesting transform, and I'll be curious to take a series of questions into a particular application area to sort of probe the opportunities for how the suddency domain could characterize features. I'll wait till...
So that's actually the remainder of the paper. We applied to the problem of the problem is to classify subjects who suffer from major depressive disorder from the control group, the healthy ones. And we achieved the same accuracy that other papers they do in a very lengthy way using, I would say, very convoluted methodology of the combining wavelets with so many different components at the end, applying the machine learning approaches, just getting the same accuracy, and we get actually very reliable estimates. The standard errors are going to be very, very, very less. They're very reliable. So in this work, I actually decided to present this transformation, even though the mathematical paper is around 50 pages, and it's going to be, it is under review, but in a mathematical journal. But I really felt this necessity, this kind of, I would say, urgency within the field of at least psychiatry and neuroscience to equip our specialists with the tools that are more interpretable. So that's the reason I actually presented the transformation for the first time within the context of EEG analysis, because I know how challenging it could become. And it is a very important one, because the major depressive disorder, when one considers that, that's a very, very, severe case. And all these disorders, the bipolar, the other ones, these are a spectrum, yeah. These are related to one another, and patients suffering from them, most of the time they are put on medications, but there's no way to actually quantify the improvement or how they are reacting to this new medication. Like the SSRIs, there are at least like 50 of them. So the psychiatrist has to make choice. Like one of them she's going to prescribe one of these and just monitor the situation for the next 3 months. But unfortunately, it's not quite obvious that how they're going to work. I mean, there's no way to quantify them. And at the in this paper, I think I really thought about it to put everything and introduce the entire transformation within like a very rigorous mathematical framework and publish it in a journal, mathematical journal. But then it just appeared to me that this domain of the signal processing, especially the one related to the neuroscience, I've seen many studies that you're not even capable of replicating the same results. I mean, because there's so many subjective steps involved that unless the person from the lab, the person in charge, comes and helps you, it is almost like impossible to get the identical results, to program the same thing and get the results. It is not portable, like the results, the program codes are not portable from one study to another one. And I see the root of this problem in the use of, I would say, the misuse of the frequency domain tools, because usually what happens is that the EEG signals, these are non-stationary signals. So if we try to analyze them using the methods which are not meant to be used, then that's going to lead to very complex methodologies with very high complexity that are not even interpretable, let alone to be replicable. So I would like to actually show this plot for the complex values, and that would clarify several points. Please carry on until I just download this.
Well, okay, so there's a related application. Well, it's not related to EEGs, but sort of, in the sense that the points you're making, possibly could map quite well into this, and it's the area that we can all relate to. It was music identification. And some time ago, I was involved in music recognition, audio fingerprinting. And in that domain, I took a particular approach that, it had several stages of processing an audio file. And it was really restricted to, identifying a particular recording. And it avoided the actual deeper subjective music similarity. But essentially the approach was to, clearly music is non-stationary, particular musical score. But it was, it would begin by small time windows using a Fourier transform and getting the power spectrum. And that linear transform, it was annoying because we don't really perceive music on a linear scale. It's linear more on a logarithmic scale. Like, if you think of the notes on a piano, those are evenly spaced out, more or less on a log scale in frequency. So, the first stage would construct the power spectrum across, and I would bend them over the musical notes on a piano. So you'd have, in essence, 72 power spectrums. And from there, we would look at a time domain analysis for each note window. And we would extract features. For example, when a guitar is plucked, there's a rapid rise in power at frequencies that are characteristic of the harmonic signature of the instrument. And, we would mark off, much like a player piano would mark off features in time, where rapid averages, and this was a stunt pulled from financial domains, where rapid averages cross slower averages as significant points in time, and characterize neighborhoods of frequency in time events, and record those in lots of little pieces, and we could recognize a stream coming over the radio by mapping consistent time windows onto these many pieces. But I'm wondering, in terms of suddency domain analysis, even if it started at the stage of power spectrums over these frequency windows that we associate with notes, the kinds of features, even if they're small features in time, but tracking how the features in the suddency domain changed over time, and whether there would be where you get a more reliable characterization of changes in power that occurred at those frequencies in time, and how that might have a more robust characterization of the musical score.
One thing about the music when you do the analysis is I think you mentioned that before, the how long a window you're going to do the for the Fourier transform, right? Because, and then also and then the nodes of music, it's only relatively homogeneous within that short time window, especially for piano, right? So I suppose that it should be more amenable to wavelet analysis than Fourier analysis, right? Otherwise, you just have to manually adjust the time window, and especially if you, let's say, you have a change of tempo in the piece of music, and then are you gonna? So it seems you have to do it manually. Would that be right?
Well, I got into developing a system that was pretty good over statistics, but every time I would present the work, be asked about wavelets, and it was one of those things. Well, they possibly could perform better, and I never got around to it but the time windows were pretty short, and I'd use a lot of them, and I'd have a detailed power spectrum built up from them, and then I wouldn't need the Fourier transform anymore. But they're still within that period of time after you've isolated the notes, and you're looking for changes in power along those frequencies. I wonder if a suddency domain could capture, because the problem with what would happen is different compression schemes of music end up giving you very different features, even though they're not really. You perceive it as the same piece of music. When you analyze,
I can actually see. I can see actually. That's a. There are two actually aspects to actually, I believe, what you mentioned. One is really, I would say, it's not really tangible what we are doing, like over there, in terms of the musical notes, in terms of what we are familiar with. And the second one, very important one, you asked actually about the power spectrum. What happens? I'm not sure about the answer, because we need to actually study that more carefully. And I certainly do not have the domain knowledge on that particular topic. But what happens is that this transformation, this Lehman transform, it is somehow, I would say, it is discrete dense. Hence, if I'm allowed to use such term, meaning that it is really like about the each particular solvency that we consider the power series, or better to say the Lagrange Berman expansion. Then that is going to fade away very quickly. I mean, it's not gonna within a neighborhood of each solvency moment, I'm going to capture almost the entire spectrum of the Lagrange Berman series. So it is, in this sense, I'm just calling it discrete dense. That's the best, I guess, description I can find. So considering such property, it means that we can see this transformation, because in another way, how about just considering our data to be continuous? So in that case, my summations in the definition of the transform would be, I can replace them by integrals from 0 to infinity, and then let's say this is just let's consider infinite sequence. Then the numerator, I can consider that to be the Mellin transform of a certain function applied to the to my sample. So, and denominator is also going to be another Mellin transform, but eventually what one finds out is that each of these components, the numerator and denominator, could be expressed in terms of the Dirac delta function, or the just Heaviside function, in a way that it is really capturing the information are really encapsulated within a very narrow neighborhood around each of these solvency moments. So considering this property of the transform, I would guess that it could potentially tackle the problem that you mentioned. I don't know if that makes any sense from the...
In a sense of capturing, for example, well, this is where the note occurred. Is that where you're going? Or because there's several time series to consider in this example. There's the power spectrum change.
Yeah, I was mentioning about the power spectrum.
Mm-hmm.
So capturing the power spectrum, you mentioned that itself is really like a challenging one to understand. Am I right?
Right. So I take 4096 windows over fractions of a second, and
true. But how many windows we need? Because there's no.
It goes to 72. 72 keys on a piano keyboard, but they'd have to be binned over a log scale. So it was already annoying because of the linear nature of that transform. But even developing the changes in the power spectrum over time and nailing characteristic points in time that are interesting features. Right?
Yeah, my answer was really it pertained to the latter part, the changes within the power spectrum, how to characterize them, because that's a very subtle, I would say, subtleties over there. How to do that? Just considering everything in a log scale, that makes the problem intangible. A little bit like we lose to some extent our insight about the problem. But when it comes to the power spectrum, then analyzing the power spectrum, that would become even more challenging. And what I was just trying to mention, that it is maybe it is possible that this property of the Lehman transform, that things, the entire series, let's say the Lagrange-Berman expansion about each of the interior points of the support, it is really concentrated about that point. So I should not expect it to, it's not like the Taylor series that I would expect it to, usually one sees that effect propagates to further away points, the points located further away. But here the property is that within a very small neighborhood around each of these solvency moments, these series, the expansion of the Lagrange-Berman, is just as if it's concentrated. It's just I don't know how to I know.
Well, you mentioned direct delta function. It's just
That was I guess the best way I could explain that. It is really because I would like to also the audience to be able to follow. So I'm avoiding using. I would really want to avoid using the words complete or anything like the Hausdorff for these kind of things. That
it looks more like a spike.
Yeah. So, but it's a spike divided by a spike. So each spike I can actually approximate that by a Gaussian kernel, right? So it would be a Gaussian divided by a Gaussian. So depending on the lag that I'm considering, one of them, the delta of the, let's say, S plus some constant C, then the ratio is going to change. So the easy way would be just maybe considering in this way. So the numerator is just going to be delta function, but the denominator is going to be the delta function. The argument is going to also have the element that can actually be added up to S. So depending on where it is located, that parameter C, the value, I might actually get considering the Gaussian kernel approximating the delta function, then I might get actually very strange and at the same time very powerful behavior to capture this spectrum. That was my point.
Okay, I ended up treating it like a financial, like a fiducial, in looking at when fast averages cross slow averages. You've applied this to financial data. I'm curious how that was, how well that works.
So for the financial data, because financial data, they have long memory. In order to convert them to stationary ones, you would usually need to apply fractional differencing, usually. And fractional differencing, it has a definition in terms of the special function, in terms of the gamma function. But so the first order differencing would be you would just find the difference of successive values in the time series of the observations. But the fractional differencing can actually, to some extent, capture that nonlinearity whenever we have the financial time series, because most of them they show this long memory behavior. But also we have other cases that we have nonlinear time series, nonlinear financial time series. For those ones, even the fractional differencing, or just considering the entire time series to be fractionally integrated, by fractional, that is not going to really help us. And if this area is still is being developed, so it is one of the recent advances. But whenever we introduce a tool in statistics, it is also necessary to introduce the required hypothesis testing procedures in order to verify whether actually differencing this fractionally integrated time series can generate stationary one for me, so that I can carry on by applying my common tools for analysis of the time series. But it turns out that there's actually time series, that the entire field itself is a new one, I would say, and there's certain there's actually there are many aspects that are not known yet, mainly in terms of the underlying distributions of the statistics that are used, because they take on I would say from mathematical point of view, they are very involved, the forms they take on. And for this reason, among others, even considering those time series as fractionally integrated, it's not going to solve the problem in many cases that I'm dealing with nonlinearity, and this nonlinearity cannot be even handled with fractional differencing, fractional differencing together with other, let's say, transformations which can be applied. So in that case, Lehman transformation also works. And my understanding is really that it deals with, first of all, the time series data, the discrete, countable observations. And it is capable of reordering somehow. It is invariant under ordering. So if I may just interpret in this way, that it finds maybe the right ordering of the data seen from a higher dimension. So the ordering that I see on the sequence, maybe it is seen in a different way from the higher dimension. And what I'm seeing is really the projection of that. Let's say it's a cycle, but when it gets projected on a line, what I see is just the sequence. So how about just considering the points that I'm analyzing being located on a cycle on a higher dimension? So in that case, this is also the idea of applying the kernels, right? You would really want to just get another view of your problem in the machine learning, so you can easily classify them. But this feature, this lemma transform, apparently, how it handles the nonlinearity is that it is as if it's considering the time series as the projection of something from a higher dimension. And I'm measuring the higher dimension because it is not really that difficult to show that the transform, once we consider infinite sequence, and that sequence are natural numbers, then one can actually write down the transform in terms of the zeta function. So it is deeply related to the zeta function, and it is actually the dual of the zeta function, in a sense.
It's sorry.
Go ahead.
So basically, it's the zeta function. Actually, I mean, you're talking about the the numerator and denominator, looking at them separately, right?
Yeah, once you need to consider the natural numbers, another time you need to consider the harmonic series.
Yeah, I mean, the only thing is it's kind of it would be a generalized zeta function, because zeta function is for the xi's to be I, right? The all integers, increasing integers. Then if it is a xi, then it's a kind of generalized zeta function, right?
Yes, of course. For the special case that we are considering the, let's say, integer values, we get the zeta, but in order to really go beyond that, we need to consider the generalized ones, or just simply the, just the generalized zeta function. So this is the transform actually is related to the zeta function, and that is related to, of course, to the prime numbers. So, so seeing things from this perspective, that some object from higher dimension manifests itself or projects itself on this lower dimensional space, and we see that as a time series, as a sequence, as I'm just suggesting just one interpretation of how this works and how it handles the nonlinearity of the time series, because it handles that. It actually works. It actually works in the domain of the financial mathematics, the same way that it works with the EEG signals. And I will, of course, proceed to the end. And I don't know, Cecil, how much time we have?
Yeah, it depends upon you. If you want to continue or you want to have a part 2, that's fine.
I don't want to actually make the audience really. I know okay. I try to be quick on certain points, but really to get to the end of the article and show actually how it worked on the EEG signals, and it will have very similar behavior on the financial ones that I've tried. And financial ones, I've tried it on the stock prices and the indices, including the uncertainty ones, like the VIX and any uncertainty indices like economic policy uncertainty index, the fiscal policy uncertainty index, and all those indices. It works quite amazing in that domain. Also, it is applicable to any nonlinear time series, but within these two domains of the neuroscience and, of course, the MDD and the financial time series, I can say that it works. It performs very well. It performs very well unless, and there's a reason for that, because it satisfies a certain equation, which turns out to be also, it appears also in the solutions of the Schrödinger equation, like the Lombard W function. That is a very, 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 I would say, foundational function. So the very fact that the extreme points of the inflection points of the transform, they satisfy properties that involve the Lombard W function. Of course, this result is not included in this paper because I really wanted to keep it to some level readable to like a broader audience. But that property, those properties, are the ones enabling this transform to have the capability to capture the wave behavior. Maybe we can take a look at the file I've uploaded, and I will come back with. Yeah, please go ahead, Harsh.
Okay. Yeah. So actually, I have a question.
Yeah.
So with respect to the times, basically,
Yes,
let's say financial time series prediction that are you, let's say, just wondering how you're done. So basically, let's say you get the sudency function over sudency domain, plot the sudency domain, and then do you let's say get n plus 1, let's say you have an observation of n sample points, and then you look at the n plus 1th data point, trying to predict that, and then so you do a Lagrange inversion from the sudency function to the x function, but then you have to.
Then I do have actually probability function to describe the behavior of the sudencies. So all I need to do, I can actually predict the sudency which is going to appear at the next point of time. And then I do have the S. I will just consider that as an input to my transform. And of course here I need to also add, I will consider that as an input, and it will give me an output. And that output will be the prediction, the forecast for the next time step.
So just trying to understand this. So you have a transform function, right? And then do you, let's say, do the derivative and get the distribution function that may be concentrated at a few points, and then you just take that point, take those points, and then invert it to get the a time series, and then is that what you're saying?
Yeah, true, but I guess it could be the procedure you mentioned is really what happens is that first we need to convert our time series into the sudency domain. So once I have the sudency domain, I would call it decomposition, the time sudency decomposition. On the sudency domain, we have all kinds of distributions. Unfortunately, I took off the paper, but it's available. It's open access. The paper is open access. The title says Theory of Lehman Transform and its Applications in Identifying the Electroencephalographic Signature of Major Depressive Disorder. But it actually turns out that you can define parametric families of non-parametric distributions. Like the ones that we defined was a very natural kind of distribution, the one which looked like logistic function. Now, on this sudency domain, once everything you inverted and you get the sudency moments, how are you going to do that? From numerical point of view, I would say it's way easier than the analytic perspective, because analytically it's very difficult to deal with, even with the Lagrange-Berman expansion. It would require you to actually, it is really one of those expansions which are very difficult to apply in real world problems. But in terms of finding the inverse of each observation, because it's going to correspond to a unique sudency moment. It's going to correspond to a unique sudency moment. All I need to do is to minimize the function, the L of S, and the observation, and the argument here is going to be, over which I'm minimizing, is going to be S, so I will find the S. So I can use actually, numerically it's easy to find those. but analytically it would actually pose some problems. So I'm coming harsh and Rajesh here. But once I have the Southern-C decomposition, then I will I will find the right probability distribution, which is described in terms of the Lambert W function, involves Lambert W function, that's better to say. And that is not going to be any arbitrary kind of distribution, but it is powerful enough to almost capture any at least form of distribution that one can consider. I mean, trimodal, even with 4 modes, 5 modes, whatever. Any kind of like weird distributions that we rarely like see in non-parametric distribution statistics. So once I have the distribution, probability distribution, then the prediction would become straightforward task. All I need to do is to just depending on the so what happens, the good thing is that both the time domain signal and the Southern-C decomposition they do have the common axis, the horizontal axis, which is the sample number, right? So the next one is going to be conditional Southern-C distribution. In order to predict the Southern-C appearing at the next time point, I would need the conditional distribution of the Sn conditioned on, let's say, if considering Markov property on n-1. So, but here we also need the global distribution, right? The unconditional one, if you take the Bayesian approach. Yeah, go ahead, Hansen.
Okay. So the Bayesian one, the conditional one is depending on the n, right? Let's say you observe n samples. Condition on that. So one segue is when you do the Lamar transform, the L will depend on n and s, or just s, and then you treat the n as a kind of implied, because whatever that it's a finite sequence, could be zero.
N is fixed, yeah. N is usually fixed because eventually we don't have like immemorial time series in reality. Yeah? We do have like finite sequences, observations. So N is treated fixed. But what is actually other parameters? We need to be careful that observations here, they are probability distribution function that can be seen at the page. The definition is given at page 7 of the paper. You see that it actually involves 2 parameters, alpha and beta. So together with the entire sequence of observations, these would parameterize my distribution. Now, all I need to do is to find the MLEs for the alpha and beta, and on the following page, at page 8, you will see that by just varying the values of the alpha and beta, you will get all kinds of different shapes of distributions. These are density functions. So these are just 2 examples here. The alpha is restricted to be between 0 and 1, and beta is a positive number. Where this comes from, I was motivated by an application that once it was presented in a seminar which was on branching processes, and over there apparently this was a problem in quantum mechanics. The functional form that you see for the cumulative distribution function of the the that is introduced in the proof. The capital F, you see some constant A plus constant B times the Lehman transform to the power of 1 over alpha times e to the power of beta times the Lehman transform. Now, those normalization constants, they're gonna appear to be in terms of the Lombard W function, and here I mean the right branch by W sub 0 or not. I mean the right branch of the Lombard function. So it is actually interesting. It is related to the waves, and that's why it is describing the signals which behave in a I don't want to use the term periodic. I would say the waves, the signals which look like waves, in a very good way, in a very efficient, very effective way, because it is eventually satisfying certain set of differential equations which are not presented in this work, and it will be elaborated on another work. But it's interesting just to see the form of the density function, or the form of the, and these are closed form. Yeah, you can, if you write down the expansion, I mean, we just plug in the L prime and everything, because we have the L prime involved at the end. It will just give you I would say complicated form of the density function, and two parameters, alpha and beta, we can find them, we can estimate them by maximum likelihood method. Yes, Rajeshi? Yeah, go ahead.
So, Harsh, can I please have been waiting? So, I wanted to ask, so is this transformation similar to Fourier transforms in that it's lossless and no data is lost, and the representation in terms of suddency moments is equivalent to the raw data array as it's stored? And can you just go into, if we consider like velocity, acceleration, jerk, are these still central moments and different from suddency moments, or can we consider acceleration to be a suddency moment? Thanks.
You're actually asking a very good question, because you're seeing from the frequency domain perspective that when you have, when you have, let's say, I would say, accelerating signal on the time domain, then on the frequency domain, it's gonna just widen the your signal, your wave. The sinusoid is going to get wider. And is that what you mean by acceleration? By the
So I think in college and school we learned about central moments theory.
Yeah.
Moments around the center, like acceleration, velocity. So I'm trying to understand how it's different from suddency moments. And if acceleration is still a central moment, or is it a suddency moment, and how, what might be the suddency equivalent of acceleration or velocity?
The answer is that I do not know. I do not know. And the answer to the first question that you asked, whether it is going to preserve the information, it is going to, it is not clear yet to me. I mean, even after all these years, it is just when you touch upon like something, I would say, relatively new. I mean, even for the continuity, it's not really easy to prove the continuity. So let alone like driving the, like applying the Fourier transform. But what I can tell is that the coefficients of the Fourier transform, they're gonna decay to zero. I mean the discrete one, they're gonna decay to zero very quickly, based on just the property that I was talking about with Serena about the musical notes. Yeah, go ahead, Anson.
Yeah, it depends on the smoothness of the original function, right? The decay rate of the Fourier series, Fourier coefficient depends on the.
Well, the Lehman transform. I wish I had some of the pictures to show you, but I don't have. It's actually pretty smooth. Like, of course, it depends on the smoothness, and we can actually construct ones. And the one thing that is really challenging here is that the upper bound on the number of the inflection points of the Lemma transform, I mean, driving that upper bound, the current upper bound that I do have is a very, I wouldn't even call that an upper bound. It just, yeah, go ahead, Harsh. Minimizing is going to be S, so I will find the S. So I can use actually numerically, it's easy to find those. But analytically, it would actually pose some problems. So I'm coming Harsh and Rajesh to you. But once I have the Southern-C decomposition, then I will define, I will find the right probability distribution, which is described in terms of the Lambert W function, involves Lambert W function, that's better to say. And that is not going to be any arbitrary kind of distribution, but it is powerful enough to almost capture any at least form of distribution that one can consider. I mean, trimodal, even with 4 modes, 5 modes, whatever. Any kind of like weird distributions that we rarely like see in non-parametric distribution statistics. So once I have the distribution, probability distribution, then the prediction would become straightforward task. All I need to do is to just depending on the so what happens, the good thing is that both the time domain signal and the Southern-C decomposition they do have the common axis, the horizontal axis, which is the sample number, right? So the next one is going to be conditional Southern-C distribution. In order to predict the Southern-C appearing at the next time point, I would need the conditional distribution of the Sn conditioned on, let's say, if considering Markov property on n-1. So, but here we also need the global distribution, right? The unconditional one, if you take the Bayesian approach. Yeah, go ahead, Hanson.
Okay. So the Bayesian one, the conditional one is depending on the n, right? Let's say you observe n samples. Condition on that. So one segue is when you do the Lemma transform, the L will depend on n and s, or just s, and then you treat the n as a kind of implied, because whatever that it's a finite sequence, could be
n is fixed, yeah. N is usually fixed because eventually we don't have like immemorial time series in reality. Yeah, we do have like finite sequences, observations. So n is treated fixed. But what is actually other parameters? We need to be careful that observations here, they are probability distribution function that can be seen at the page. The definition is given at page 7 of the paper. You see that it actually involves 2 parameters, alpha and beta. So together with the entire sequence of observations, these would parameterize my distribution. Now, all I need to do is to find the MLEs for the alpha and beta, and on the following page, at page 8, you will see that by just varying the values of the alpha and beta, you will get all kinds of different shapes of distributions. These are density functions. So these are just 2 examples here. I mean, the alpha is restricted to be between 0 and 1, and beta is a positive number. Where this comes from, I was motivated by an application that once it was presented in a seminar which was on branching processes, and over there apparently this was a problem in quantum mechanics. I mean, the functional form that you see for the cumulative distribution function of the that is introduced in the proof. The capital F, you see some constant A plus constant B times the Lehman transform to the power of 1 over alpha times e to the power of beta times the Lehman transform. Now, those normalization constants, they're gonna appear to be in terms of the Lambert W function, and here I mean the right branch by W sub 0 or not. I mean the right branch of the Lambert function. So it is actually interesting. It is related to the waves, and that's why it is describing the signals which behave in a I don't want to use the term periodic. I would say the waves, the signals which look like waves, in a very good way, in a very efficient, very effective way, because it is eventually satisfying certain set of differential equations which are not presented in this work, and it will be elaborated on another work. But it's interesting just to see the form of the density function, or the form of the, and these are closed form. Yeah, you can, if you write down the expansion, I mean, we just plug in the L prime and everything, because we have the L prime involved at the end. It will just give you I would say complicated form of the density function, and 2 parameters, alpha and beta, we can find them. We can estimate them by maximum likelihood method. Yes, Rajeshi? Yeah, go ahead.
So, Harsh, can I please? I've been waiting. So, I wanted to ask. So, is this transformation similar to Fourier transforms in that it's lossless and no data is lost, and the representation in terms of suddency moments is equivalent to the raw data array as it's stored? And can you just go into, if we consider like velocity, acceleration, jerk, are these still central moments and different from suddency moments, or can we consider acceleration to be a suddency moment? Thanks.
You're actually asking a very good question, because you're seeing from the frequency domain perspective that when you have when you have, let's say, I would say accelerating signal on the time domain, then on the frequency domain it's gonna just widen the your signal, your wave, the sinusoid is going to get wider. And is that what you mean by acceleration, by the
So I think in college and school we learned about central moments theory. Moments around the center, like acceleration, velocity. So I'm trying to understand how it's different from suddency moments. And if acceleration is it a central moment, or is it a suddency moment? And how, what might be the suddency equivalent of acceleration or velocity?
The answer is that I do not know. I do not know. And the answer to the first question that you asked, whether it is going to preserve the information, it is going to. It is not clear yet to me. I mean, even after all these years, it is it is just when you touch upon something I would say relatively new. I mean, even for the continuity, it's not really easy to prove the continuity. So let alone driving the applying the Fourier transform. But what I can tell is that the coefficients of the Fourier transform, they're gonna decay to zero. I mean, the discrete one, they're gonna decay to zero very quickly, based on just the property that I was talking about with Serena about the musicalness. Yeah, go ahead, Thompson.
Yeah, it depends on the smoothness of the original function, right? The decay rate of the Fourier series, Fourier coefficient depends on the.
Well, the Lehman transform. I wish I had some of the pictures to show you, but I not have. It's actually pretty smooth. Of course, it depends on the smoothness, and we can actually construct ones. And the one thing that is really challenging here is that the upper bound on the number of the inflection points of the Lehman transform, I mean, driving that upper bound, the current upper bound that I do have is a very, I wouldn't even call that an upper bound. It just, yeah, go ahead, Harsh.
Yeah. So when you are discussing about, let's say, a story, it's actually really sorry for. So I'm outside. So if you are looking at the story, it's actually words, which is one variable, time, which is another variable, and space, that where the position is. So let's say we are discussing right now. So you are talking about numbers. This is one variable. The words in alphabet, which is one variable, and time series, the time. So the other people who are looking at this conversation right now, they have their own knowledge and they interpret in their own way. Some might not get what I'm trying to say. Some might get what I'm trying to say. So I'm talking about perception here. So let's say a wave function of speech is x, comma, a, comma, t, where x is the space variable, a is the alphabet variable, and t is the time series variable or time variable. So can we convolute with another function that will develop in an AI, or between us that I have my own function, to understand and have a coherence of speech? Are you getting my point?
Yes, I do see your point, and that's actually a very deep question. The issue here is that...
So, can we do this? The question is that can we replicate this in AI? So, by the quantum wave model of the brain.
Sorry, what was the last thing you mentioned? Can you come again?
So, if I see, humans are actually quantum function because their decision and their state is not 0 or 1. We are in multiple modes and multiple emotions. So I define that we are not 0, 1, we are quantum functions. So if we can replicate an AI which has a decision tree like state 1, state 2, state 3, and going to state 2, like excited, non-excited, angry, not angry. So can we replicate
Are you referring to the hierarchical models that the AHPs that we have? I'm just kind of lost where you related to the consciousness, because over there we need to be a little bit careful. Is that
yes,
the question?
So what I'm not going to consciousness, it's mostly about taking one, like I'm at a decision, let's say I want to buy a product. I get an advertisement, I get excited. It might be K. Also, it is still neuroscience, leaky capacitor, and logistic growth function, how the neurons work, decision-making state. So the same way, my understanding of the world, as a story I am seeing, and you are seeing the world as your story. When we communicate, so can we explain each other what we both are seeing, so that there is no dissonance, actually a coherence?
Okay. Because you actually, there's certain elements in this question that are kind of very difficult to even relate within the domain of the frequency, where you can define the incoherence and everything. But right now we are dealing with, this question is actually, okay, as long as we are thinking in terms of the frequency domain, it would be difficult to really see the advantage, the benefits of working on the solvency domain. I mean, I can see your point of view definitely here. You're trying to see whether it's possible to map one problem that exists over there, or one phenomenon that exists over there, to some phenomenon which might exist on the solvency domain, and it could be much easier to analyze it on the solvency domain. Am I right?
Yeah. So the same way the time series can be like time in seconds and milliseconds. It's like a discrete version of. Actually, my question is with the continuity. That continuity is actually a subset of some higher dimension. Because essentially so time is also like space-time variable x, t.
Yes.
So time is t projection at the time axis, and x space axis also. So when we are talking about this, so
as long as you have the state, I don't know if this answer helps. As long as you have the state space representation of your signal, I mean, you don't need to even have all these steps being evenly stochastic being defined on periods and on steps that are equal in distance in measure, in Lebesgue measure. Their length. Then, as long as you have the state space model, you are always capable of expressing that on the solvency domain. That signal can be expressed. But in terms of the properties that we are familiar with, like the powers, not just properties, like the power spectrum, the coherence, these concepts are very, very actually difficult to to even investigate how they are related to the other one, and this is really work in progress. So, please go ahead.
Yeah. So just one more question is that when you deal with nonlinear dynamical equations, and let's say I have three-dimensional system of equation or nonlinear system equation. So when I want to do parameter estimation and prediction, will clubbing two variables together, or is there any way a transformation which can help me to actually estimate and fit the data and get the values? So all I can do is qualitative and quantitative analysis.
Did you mention you have two variables?
Yeah, so let's say I have two dependent variables and one independent variable.
Yeah, we have no problem with that. There's no
let's say I put
assumptions.
Another third variable, which is function of first two variable and an independent variable.
It's okay.
So how to deal with
that? That part, it can handle. It doesn't require the observations to be realized from identically and independent samples.
So which theory can I use to actually understand any sampling measure, like some numerical method that can be used for the data fitting and prediction?
They can potentially be used, yeah. And the very first example that they talked about, that how natural it is to construct probability distribution functions, but using the data. I mean, that is not something really, it's not, the result now is trivial to see, but that is something I would say near impossible without having the right tool, without seeing things from the right perspective. So in terms of the data and the relations, the dependences different, dependence relations. We should not be concerned about those, as long as we are dealing with the observations. And here we can have complex valued observations as well. That would require another type of treatment. But real valued observations, as long as we have them and they are positive, strictly positive, if not, using the transformation that I've mentioned in the paper, that would convert them to the positive ones. Then you do have you can do everything with those observations. You can come up with the probability distribution functions which can actually express, which can describe the behavior of the suddency moments themselves, showing that what is the likelihood of, what is the probability of observing the heavy tails statistics, like the maximum. This is actually relating to the area of the large deviations. So it is really giving me the probabilities on the statistics, on this domain of statistics. It's telling me what's the probability of observing the minimum number, minimum statistic. And then here we don't have a problem. So let's say your time series has been realized from a stochastic process where the comprising random variables, are not identically distributed, neither nor they're independent, nor are they independent. So here we don't have a problem as long as we're dealing with the realization, with the numbers, actual numbers. But if we replace those lowercase x's with uppercase x's, meaning that I consider them to be random variables, and that would be really exciting part, because I can drive the distribution of the sample mean, and this distribution is driving the distribution of the sample mean itself is a challenging task. And all we have, the best tools that we have are the laws of the large number, the law of the large numbers and the central limit theorem, which hold under certain conditions. But here, without requiring any conditions to be satisfied, I can actually drive the distribution of the sample mean. Not only sample mean, any statistic within that range, and any statistic in general, I can drive its distribution. I do not need to resort to the central limit theorem. I do have the exact distribution, but that would require me, sorry for interrupting, that would become a very challenging problem if I do not make an assumption of the IID. So even making the assumption of the IID, that would lead to very challenging problem. You're definitely going to use the Stochastic lemma. So you have the convergence in probability, you have convergence in distribution, hopefully, in one of the values, because we always have the ratios involved. Summations or subtraction of ratios multiplied by other ratios. Here, in order to derive the distributions, it is, I would say, it's practical to consider those assumptions. Yeah, go ahead.
So it's like a perception equilibrium from 2 point of references, or a probability distribution if you see it.
Yeah, to some extent. Yeah.
So it's more like that from 2 frame of references where the signal is perceived differently. We can have an equilibrium probability distribution overlapping where both the two reference frames are somewhat getting the same point. It's like you telling us a story and we all reaching to the same conclusion.
As long as you have the deterministic samples, I mean, you have the realizations, we all reach the same conclusion, if that's what you mean. But
yes.
From statistical point of view, especially from probabilistic point of view, it could be a much interesting problem to just consider the stochastic process itself instead of its realizations. So instead of time series analysis, which was really focus of this paper, we just replace them by the random variables. Then the first question would be, what is the distributions of these random variables? And it turns out that we do not actually need to, in any problem, you would usually first dive into the limiting distributions. You would first attempt finding the limiting distribution of the your random variable. But here, because as long as n is greater than or equal to 2, you have more than one sample, you can actually derive distribution.
Yes, true. Thanks a lot.
So, yeah, sure. Rajesh, you have a question?
So one of the useful properties of Fourier transforms is that after I derive the Fourier transform of, say, 10 data points, when I get the 11th data point, I can apply a trivial operation to get the Fourier transform of all 11, right? So my question is, can you do the same for Lehman transforms? Like, I take the Lehman transform for 10 points, and then it's like when I get the 11th point, I don't have to calculate it again for all 11 points, but I can just do a simple operation with the 11th point to get the equivalent transformation for all 11. Is that the case?
That is not the case. We need actually to augment that new observation with our already observed sequence. But what happens is that this online, I would say the online updating, the cost is really negligible. All we need to do is to add one term to the numerator and one term to the denominator. So for the very large data sets, like 24-hour recordings of the EEG signals, once I do obtain the probability distribution functions of the Lehman transform itself and its inverse, which gives me the suddencies, then updating that is going to be costless, almost costless. But it is not certainly like the Fourier transform. You need to compute it.
Got it. So then in these scenarios, another advantage to FFTs is that you get hardware accelerators like fast Fourier transform chips, which is why it's so prevalent in the industry today. So I guess my question is this, since you can't adapt and add new variables, you have to recalculate the distribution or the transformation every time. Is there any possibility of hardware acceleration for this transformation so that it'll be more efficient in the future?
In terms of the hardware, okay, as I mentioned, it is costless to update this distribution.
Oh, I'm so sorry. Could you explain how?
Yeah, it's just like the computation, the complexity is not really high. I do not have actually the results to mention that, but it certainly has there's a complexity involved, but the complexity is not a high complexity. And besides, there's another point here. If I have 1 billion observations already in my time series, and I add one more observation, then the impact of this additional observation is really going to be negligible. So I'm not expecting to see a drastic change in the behavior of the suddency moments and the corresponding distributions. So for the purposes of the financial time series, where the portfolio optimization, let's say, is concerned, one can really deal with, find the distributions, probability distributions, and just deal with them until enough number of points, enough number of observations are gathered, then update the distribution. Yes, please go ahead.
Oh, right. So you can do the batch update, but you do have to do a recalculation. I understand that it's not very expensive complexity, right? Just a question around like order of moments. So I noticed that the suddency moments are all first order moments. I think from central moments, sometimes we do things like take the second order, third order until one of them tends towards zero, like limit tends to zero. So I guess the question is, is there any purpose or point in calculating higher order moments for suddency moments as well?
Yes, that's a very good question, actually. So what happens is that it is not the higher order moments that are involved here. It's going to be the terms, multiplicative terms involved. So the higher moments are going to somehow manifest themselves in terms of multiplication of log terms. Results which would remind one from results that we are familiar from number theory or the Kolmogov's, some of the works of Kolmogov. It's just it certainly finding the higher moments, they're valuable, yeah. But what I'm trying to say is that this transformation, as far as I've gathered how it works, is that it is not the higher moments in terms of the integer valued exponents that are going to really be involved. It's going to be multiplicative terms where the log terms and the log terms and the log terms are going to be involved. So it is doing something, I would say, rather different when it comes to it. But that's a certain valid question, and we can actually compute the variance, because the variance we can compute that. In order to compute that, I need the second moment, and the second moment, the interpretation here. So the second moment really, the first moment describes let's say the center of the gravity. Yeah, the second moment is really describing if I consider some topological object being associated to these random variables, okay, then the second moment always describes the size of this object, whereas the third moment, which is also called we can define the curtices based on that would describe the shape of that, let's say, I'm reluctant to use the geometrical shape. I'm just referring to some topological object. Okay, so that has a meaning. Certainly it's meaningful to compute it, and we need to compute it in order to find the variance, in order to check basically the Kramer lower bound to see whether it is attained or not, and to compute the differential entropy, find the Fisher information. We're gonna need all those info. But what I found it worthwhile to mention was that it is really somehow this transformation, I mean, especially its probabilistic behavior, is gonna it's gonna depend on the powers of, the exponents of the these s values being placed on the exponents, but also the log of the terms and the log of the log of the terms and the log of the log of the log of the terms. At least up to 3, I can confirm that it is possible to derive, like, certain properties are derived in these forms. So these results are not really, first they seem strange, but when one realizes that even we can express this transform in terms of the zeta function for the at least special case, or if we consider the generalized case, then it is not really far-fetched to be able to do such thing.
So when you say logs and logs, are you referring to the asymptotics of the transform?
Not even asymptotics. What happens? So we expected to see those terms in the asymptotics, at least in number theory, yeah? But what happens is that they appear whenever you want to actually derive distributions themselves, or the properties of the distribution. So it's not just the asymptotics. You know what I mean, Hansen?
Not sure, actually. Where does it come from?
Maybe you have the paper?
Yes.
Okay, can you please, I guess you were driving when I was mentioning that. Can you please?
Not now, so I can read it. Yeah.
Okay, let's do something, Hansen. I guess it would be really, it might be helpful. Let's take a look at the picture I've uploaded here. So this image actually shows the complex valued version of that. But I'm still dealing with real valued observations. So the observations I have are just 2, 3, 4. 3 observations I've made. And let's see what happens if I consider my suddency moments to be complex valued. Okay. The plots on page 3. Hansen, this is actually going to explain why the log terms appear and what I mean by them. Okay, the x is actually the real part of the suddency moment, and y is the imaginary part of the suddency moment. So when y equals to 0, if one pays attention, you will see that logistic behavior, that if at least moving from right hand side to the left, you will see that x is showing me the suddency moments, the real suddency moments. For instance, x equals to 0, that corresponds to the harmonic mean. X equals to 1 corresponds to the average. X equals to 1 over 2 for the special case of sample size being 2 corresponds to the geometric mean. X equals to 2 corresponds to contour harmonic mean. And it's quite obvious that apparently everything is happening about that strip from somewhere from -half to, I would say, maximum like 2. So the first, the plot on the top is the real part of the Lehman transform, and the one on the bottom is the imaginary part. But interesting thing to notice is that it becomes flat as x approaches infinity or negative infinity, and this explains why it is so difficult to characterize the large deviations, to deal with those extreme value distributions. Here we can see that the sample is providing me with no information. I don't see any curvature. It's a flat, almost flat surface, right? So that flat surface, the Fisher information and also the entropy, we can always see them to increase whenever I have sharp peaks in my probability distribution. Okay. Now, any plane that I consider cutting this 3D plot from at different y values, which are the imaginary part, is going to give me one distribution. But unfortunately, the only valid one in terms of Kolmogov's axiomatization is the one corresponding to y equals to 0. Nevertheless, we can always have this perspective that when we see flat functions or flat surfaces, the information is near 0. And this actually explains to some extent why it is difficult to study the large deviations. At the same time, it explains something very interesting, that why even the central limit theorem should be in action. Because as you can see, I don't know if you can find the point x equals to 1. Maybe
on the real axis for the upper plot?
Yeah, let's go to the next page where we have the contour plots. I think that would be that's much enlightening. So things are really happening within this strip, from negative, I would say, half or 1 to 2. Within this strip, the data and the observations. It's quite actually fascinating that, here we see a spectrum. Let me be more precise. So for each statistic, previously, what we had was a simple average. Now for the average, I'm showing that there exists a spectrum. For harmonic mean, there exists a spectrum. So these are actually very important information in terms of seeing that when the statistic approaches to the S goes to the infinity, the real part, where I'm expecting to study my goal is to study the large deviations, the heavy tail properties. There's little to no information available, whereas within this strip between -1 and 2, almost all information are concentrated. So it is also reflected both in the real part. Of course, it has different interpretation than the one we see, the contour plot that we see at the bottom. Yes, go ahead.
I'll correct my interpretation. It's like if you see the mean is 5 plus or minus 0.5, you are helping to understand that plus or minus 0.5, how much is the tendency to be what exactly? You're breaking down that interval, is that correct?
Okay, let me tell you something. Observing 5, the probability of observing 5. Okay. Contra harmonic mean is such a robust estimator with respect to sample points which have small magnitudes, that I would really consider that close to the maximum. Okay, so S being equal to 2, or real here X being equal to 2, has a very, especially 3, or the case that you mentioned 5, I would really see that as its behavior very close to the behavior of the maximum statistic, because maximum is the most robust estimator with respect to any small value, right? If you change any of those values, it's not going to, it's not sensitive. whereas sample mean is the least robust estimator. You change one of the observations, you change, you add like one extremely large value, it's just gonna pull like the entire center of the the average to like in a very drastic way. I mean, one observations can have very, very significant impact on the value of the average or sample mean. So sample mean is the least robust estimator, whereas the harmonic mean is a very robust estimator with respect to large values in magnitude, of the observations. Now, since you mentioned 5, I would, depending, of course, it depends on the data, but when you, if you work with these, this transform for a while, you will just notice that after certain suddencies, you will just keep observing the behavior of the maximum and the minimum. So there's really not that much of difference. So everything is really happening within that narrow strip. And that coincides with the strip that the central limit theorem is formulated on. Central limit theorem, that corresponds to the case of x being equal to 1. But interesting thing is that now for x being equal to 1, we can see that there exists actually a spectrum of statistics. It's not just one sample mean. There's a spectrum of sample mean that manifests itself on the imaginary part of the transform. The suddency moment.
When you say spectrum of mean, is it something like eigenvalues? Is that a close approximation of what
Let me give you a better something very close. Like the hyperbolic sine function. Okay, it doesn't look like a sine function, but if you look at it on the imaginary axis, you're gonna find the sine function. Okay, this is something, of course, the closest thing that came to my mind. Maybe Hansen can help out here. But what I'm trying to say is that right now I defined infinite number of the infinite of the real numbers, infinite number of statistics. But even for each of those uncountable number of statistics, I'm saying that there exists a spectrum, and this makes it very interesting. Very interesting. So if you want to really study the apply the Fourier transform or anything, we need to consider these kind of of course, it should be the complex valued version. So the general formulation is in terms of the complex value. Yes, go ahead.
Can I just trying to wrap my head around this? So suppose we have 3 numbers, 1, 2, and 3. Traditionally, the mean would be 1 plus 2 plus 3 is equal to 2. But a spectrum of means would be like the mean is 2. Suppose we get another variable 5. So it's 2, 3, 4, 5. Now the traditional mean might be say 3.5, but the spectrum of means would be 2 and 3 and some complex valued spectrum of means. Is that correct?
No, the spectrum is gonna it's gonna be a wave. This is a wave, what we see here. So you give me two observations, I will construct a wave for you, a wave function, a complex valued wave for you. Okay. So the spectrum is really observed on the imaginary part of the function. Maybe you can go to the next page.
Okay, got it. So just instead of saying 2, we would say a wave function that approximates to 2, right?
Maybe it will help. Tell Rajesh that basically so S when S is 1, it's arithmetic mean, and then when it's 2, it's the well, actually 1/2 is the geometric mean, and then 2 is harmonic mean. So that kind of that's the spectrum of means that Masoud is talking about, right, Masoud?
Yes, exactly. For each of those means or statistics, these are statistics, yeah, we have this spectrum, which is actually on the imaginary axis.
Okay. The spectrum represents the real values that the mean could take, that each of these means could take?
Yeah, for each of the real valued means, these are not means. Like maximum, I wouldn't call it a mean. This is just called a statistic. Yeah, any of these are called statistic. Like the sample mean, the harmonic mean, these are called statistics. Any of these statistics, it has actually a spectrum corresponding associated to it, and it turns out that the most informative spectrums fall within the strip that is really the strip that the central limit theorem and most of the important theorems, at least, they deal with. So I was just trying to explain why those log terms appear out of nowhere without even dealing with the asymptotic Hansen.
Actually, I mean, I think, yeah, I'm still, not completely clear about the log. Maybe it'd be clear. Maybe like, do you have a like explicit formulation of that terms? Let's say maybe another paper or something.
Yes. As I mentioned, the lengthy paper is actually under review, but I will actually go back to the main paper. I will give you the intuitive, the insight behind that. Yeah, but let's also see the page number 5. I'm
That's
considering
the paper
now.
Page or the
No, the same paper, the same as page number 5. Now I'm considering more observations.
So sorry, is that the note page or the paper page?
Yeah, the same one that we have the figures, the contour plots and the
Gotcha, okay.
the complex valued, yeah. So right now instead of considering 3 observations, I'm considering the prime numbers from 2 to 17, which comprises 7 numbers. Yeah, 2, 3, 5, 7, 11, 13, 17. Let's look at the behavior of this. It suddenly becomes much more clear that as approaches, the statistic goes towards the either tails that we have, there is less information to deal with that statistic. And this is how I understand this, that why the area of the large deviations, the theory of the large deviations, becomes sometimes very challenging in order to apply and study. But again, pay attention to the neighborhood around 0 or maybe neighborhood around 1. It is just all those important
maybe another paper or something.
Yes. As I mentioned, the lengthy paper is actually under review, but I will actually go back to the main paper. I will give you the intuitive, the insight behind that. Yeah, but let's also see the page number 5. I'm
That's
considering
the paper
now.
Page or the
No, the same paper, the same as page number 5. Now I'm considering more observations.
So sorry, is that the note page or the paper page?
Yeah, the same one that we have the figures, the contour plots and the
Gotcha, okay.
the complex valued, yeah. So right now instead of considering 3 observations, I'm considering the prime numbers from 2 to 17, which comprises 7 numbers. 2, 3, 5, 7, 11, 13, 17. Let's look at the behavior of this. It suddenly becomes much more clear that as approaches, the statistic goes towards the either tails that we have, there is less information to deal with that statistic. And this is how I understand this, that why the area of the large deviations, the theory of the large deviations, becomes sometimes very challenging in order to apply and study. But again, pay attention to the neighborhood around 0 or maybe neighborhood around 1. It is just all those important, if I may to say, events, important parts, these spectrums, these are really the ones probably leading to the something phenomenon that we know it as like central limit theorem. So it is really things are happening within this strip.
I understand. I agree. So, but the log, is it at the large X range or within that?
Okay, let's go back to the paper if it's possible. Page number, the page number 4 of the PDF file of the paper. These results, I will, they're under review, but once at least the first time I just tried them, they really reminded me of very similar results, like from the number theory and probability. You see this form of the derivative of the transformation at the very last line. If you pay attention, for any pair of observations, I do have I do have all the important mathematical, algebraic operations and functions involved.
So basically, the log you're referring to is the log of X, right?
Yes. The log I'm referring is the log of the observations.
Okay.
Log of X.
I thought you were saying log of S. So
no. Log of the observations.
Okay.
Yes. And actually, that's why it is related to the number theory, because also over there we have the positive numbers, right? So we are always able to apply the log.
Yeah.
Log function. Yeah. But it's interesting to just notice that I do have this subtraction of these pairs of observations at the same time multiplied by the log of the ratios, and then multiplied by the pairwise multiplications of them, raised to the power of the southern-C moment minus 1, and if you want to maybe get a better understanding, that minus 1 could be replaced by plus I squared. And of course, it's not really helpful here to see the, how that can relate. But just saying that, all these terms are involved, all these operations, algebraic operations, and the functions, two important functions are involved here. That is I would actually love to hear your feedback, of course from the audience, what they think about this.
Yeah. So, but originally, because I thought it was just asking about log, because I thought it was the change rate of change, but then the log is the observation. So I don't know.
Hansen.
Hansen,
this is
no. I understand it's a log of.
No, just look at the line above. you know, this is just special case of the first order differentiation. If I want to find the nth order derivative, then I define the lambda to be the log of the transformation itself, and the expression that you see on the formula above that.
Yeah, no, I see your point. The general derivative that looks like basically the binomial summation.
It just looks like, but pay attention to the derivative, the partial derivative, and because the first derivative, we can always express them in terms of the lambda. The first derivative is going to be lambda prime divided by lambda. True? I mean, L prime is going to be equal to lambda prime divided by lambda.
Yeah.
Mm-hmm. Then the second derivative is going to be the L prime of S is going to be L, the Lehman transform multiplied by gamma prime. Okay, I mean the third, the second derivative multiplied by bracket gamma double prime minus gamma prime to the power of 2. Close the bracket. Okay, and this way, if we continue, and that formula is really just showing that, it is quite interesting to see all these log terms appearing, and here actually you will see the log terms appearing, and it will appear since you take in derivative, it will become the chain rule, so they will actually even show themselves just in the derivatives, let alone the other properties that we derive.
Link the paper, the main paper, to the top of the room again, please. I think
Yes, absolutely.
And is there an inverse Lehman transform? Like, if I've calculated the transform, can I, to reasonable accuracy, get back my statistical distribution?
Analytically, you should get the exact same because it's an invertible function.
Oh, super cool.
Yeah, as long as you have the compatibility condition on your sample, meaning that not all the sample points are equal, and if you have actually real valued samples, then that condition is already satisfied. You will never observe you will never realize two observations that they are equal. So you already have the compatibility condition satisfied, and you're going to get unique sudencies being associated to each one of these statistics.
Just a mathematical curiosity. If you have two convergent series, convergent series, basically, both infinite summations, do you still have the the inverse invertibility?
By convergence?
Oh no, the summation is infinite.
Yes. The good thing is that this is a ratio. Okay, so we don't need to really be careful. This is mathematically, it needs to be
sure. Each of them don't have to be convergent, but the ratio, so long as the
ratio is going to take care of. But mathematically, we need to be very rigorous in this, like how to actually deal with it.
Yeah. So, but
can I?
So do you still have the invertibility?
Yes, you do have the invertibility.
Okay.
Can I ask? Sorry, go ahead.
Go ahead, Rajesh. I'm done. Yeah.
I just want to ask, what other invertible functions are there? Invertible transformations like the fast Fourier transform, like the Lehman transform, which are analytically invertible?
You have all those associated, but equivalent to the Fourier transform, right? The Laplace, the Mellin and all the other kind. Yeah.
But this is not equivalent, right? So it's of a fundamentally different nature, if I understood correctly.
Sorry, say again.
The Lehman transform is not fundamentally equivalent to the Fourier transform, right?
No, it's not.
No, it's not. It's different. It's actually very difficult. To my understanding, if one tries to look from the lens of the frequency domain that we are familiar with, it will become very, very difficult to make a connection to the transform. One needs to see things from really the statistical domain. And then it's just another point of view. So the other ones, the Fourier transform, the Laplace transform, Mellin transform, these are all related, yeah. But this one is actually, to my understanding, there hasn't been any statistical transform like defined in this way. At least dealing with statistics in a very direct way. I'm not aware of any, but dealing with the statistics very directly and defining a spectrum for each of these statistics, that is, I believe, is unprecedented, unless it has been defined. That's to the best of my knowledge. Yeah, go ahead.
And could you point me to maybe other classes of transformations, like Fourier and Laplace is one distinct class and Lehman is one distinct class, maybe other approaches or other analytically reversible transformations?
Yeah, the thing is we don't have those many transformations in mathematics. There are transformations, but eventually most of them are just related to the Fourier transform. But so the Lemma transform, I would consider that to have a different nature, but I'm not aware of any other transformation, because so far the transformations were either defined on the time domain, and here time is just a dummy variable. Yeah, we mean indexed. Okay, the time is just another label for the index, and the transformations dealt with the frequency domain. So this one is different in nature because it deals with the domain of the moments which generate statistics. So there's a fundamental difference here. But to answer your question, if there are other ones, to be honest, there's just very few transformations. Like you have rate transformation, you have you don't have you have really a handful of transformations. So and most of them, they have some desirable properties, like the ones that you mentioned. The ones related to Fourier transform, they all have those nice properties, if that answers your question.
It does, thank you. One last question for me. So my understanding is that the most, I would say okay, so complex data, when do we get complex data? Quaternions in things like fundamental analysis of physics or biology, chemistry, simulations are I think a common use case. So is this helpful for doing things like the evolution of quantum systems and simulations around that?
Okay, let me then, I guess it would be a very good idea to just wrap up this discussion in a few minutes by showing the results, how it works on an actual problem, which is a very complicated problem. Okay, so if we just scroll down to page number 8, here it starts the description of the major depressive disorder and how the measurements were gathered. And it turns out, actually, I do have missing data. And these missing data, please pay attention that these are not just missing data from time series. These are missing time series. Okay? As if I'm missing 1 billion data at the same time. The entire time series is missing.
So this transform does not it works with the missing values. There's no problem with the missing values. So the table you see on the next page number 9 from the PDF file, you see in total you have like 6% of the data missing. This 6% is a lot. It's a lot. 6%. So then what one needs to do is to define a tensor, basically, because now you're dealing with, in this case, we have 2 experiments, and in each experiment, there's 64 channels recording the EEG signals, and I do have also a certain number of subjects, so I do need a 4th order tensor in order to embed all this information. But once that's just a representation here. Of course, you can also take advantage of the different tensor operations, in particular the tensor regression and tensor decompositions, to find very interesting properties. But the features which are important for this problem, they are going to be the terms which really look like the differential entropy of a distribution. But the M1 and M2 are going to be the modes of the distribution. If we move on to the next page, I will show why these modes, and even if you look at these plots, I'm pretty sure it is possible to even see from these 2 patients how different things are, how different the frontal lobes of a patient suffering from major depressive disorder works from a healthy one. The green plots that we see, so this is an experiment with 19 channels, right? So I do see 19 plots, and these plots, each of them correspond to the grid that you see over there. I think I misspoke. I mentioned temporal. Did I say temporal or frontal? I meant temporal. Yeah. So I'm just correcting myself in case I misspoke. So the plots, the subplots we see on the top, they correspond to healthy subjects. Whereas the ones at the bottom of the page, the ones depicted in red, they correspond to patients with MDD, with depression. Okay, one thing you can notice, and this happens, if I plot it for all the patients, you will see more or less the same behavior. You see how the healthy patients, the green ones, they are more or less unimodal distributions. They have only one mode, and mode is where the distribution becomes maximum. It is the extreme, the point corresponding to extreme of the distribution, where the first derivative becomes 0 on the PDF. But when it comes to the red plots, you almost all the density functions, they are bimodal. They are bimodal distributions. So the limit transform actually provides you with a very good pictorial way to see these signals, which otherwise are seen once they plotted, they would look like something I would say it's very difficult to even take a look at the time plots of them and make sense of anything unless you apply like some transformations. But the lemma transform, especially the distributions defined on that, makes it possible to just visualize these signals in a way that is very informative. It's very informative. I mean, I can tell by just looking at the red plots that this patient is most likely the one with MDD. Now, how to quantify that, to what extent the medication. So one task would be just do the classification to discern the healthy patients, say healthy subjects from the MDD patients. And as you see on the next page, table number 4, so there are different methods. The competing one, which actually we are using they've done all the measurements. It's a medical study, and they've done the analysis, and they apply the wavelet transform with rather I would say the procedure is very involved. So the accuracy they get is 87.5%. And considering that how many elements are involved in their method, their method is very powerful and it's very well thought. And the measurements and the design of the experiment is an excellent one, and that's actually what enabled us to work with a very reliable data. But the fact that the wavelet transform, in order to apply it, you would need to define so many other components, and eventually you get 87.5% accuracy, which is impressive compared to the previous methods, if you see. But now, within just, I guess, 2 pages that I'm using just one, I'm only using 5 features from page 9 of the PDF file. The ones which look like which are not the differential entropy, they look like the differential entropy. They have the same form. With these 5 features, 3 of them they have that, and the other ones are just the cumulative distribution up to the first mode, and the cumulative distribution, the probability to the right-hand side of the second mode. With these 5 features, if you run any classifier, you get almost identical results. Like if you run CNN or BADT or GMB, the entire purpose of putting that table is that the results are not really that sensitive to the choice of the classifier. Rather, it is just the transformation itself and the probability distribution have captured those salient information from the data. And here, any classifier can do the job. It just depends how one wants to do it. So if one used like the bootstrap aggregated decision trees, you get very good results. The same way that if you apply the CNN and also the Gaussian naive Bayes. So these 3 methods I've reported here, and you see they almost yield the same accuracies. So the best accuracy that I'm reporting is for the you can see at the bottom of the table 4, with almost 94% accuracy. We can discern subjects suffering from MDD from the healthy ones. But also, we can quantify to what extent a patient who has MDD, is showing some improvement, is reacting to the medication. And how to do that? Well, next page, on page 12, these are the differential entropies of the entire distribution now. The PDF, we consider that, and the differential entropy. And if you take a look at the temporal lobes, which correspond to T4, T6, at least the right temporal lobes. I mean T4 and T6. Let's take a look at these ones. As you scroll down, just compare the first the first plot with the second one. The first one corresponds to the major depressive disorder subjects, and the second one corresponds to the heat map of the control group. But you can obviously see that the differential entropy is actually quantifying. It's quantifying whether I wouldn't call it a biomarker at this time, because that would be a big claim and that would require a lot of work, and that is beyond my expertise. But this certainly, the differential entropy itself, it tells me that the temporal lobes of the brain are engaged when somebody is suffering from major depressive disorder. Especially if we go to the very last page number 14 from the PDF file. And this is actually, in a sense, it's ironic to see this result, because the patients, they have been asked, to perform a task. And when performing a task, it seems that, based on the results, it is evident that the amount of activity in the brain of those with MDD reduces compared to the case that their eyes are just closed or their eyes are just open. So this task is that they have a monitor in front of them and some shape appears. They need to actually just recognize the shape and do simple tasks, like there's 3 shapes. But the irony is that one would expect that when performing a task, the person's neuronal activity should actually rise to some degree. But it's the other way around. The patients with MDD, when performing tasks, they show less brain activation. And this really, the last plot, the one on the top, that helps us to detect which part of the brain is really engaged. Of course, most the brain is a very, very complex. It has a very complex structure. It's not just we can just easily relate things. But if one takes a look at T4 and T6, you will see, especially T6, which is the right frontal lobe. Right temporal lobe. You will see almost there's no color, which I would say it's they're all faded. At this column, all the colors are faded. So each row that we see here corresponds to one of the patients in the MDD group. So all MDD group patients, they share this common feature that their temporal lobes shows almost no activity when they are performing a task. And let's bear in mind that we always have misclassification error involved. So you can see one row that is not really following the same pattern, but that is really because of the misclassification. That's why we never get the 100% of accuracy. Yeah. So among these MDD group, there are also healthy subjects. But if you look at majority of them, you will actually figure out this pattern. Whereas, let's say, for the frontal part of the brain, there exists actually the activity we can see the activity is higher. So just compare it with the heat map at the bottom. This is for the healthy subjects. And again, there are some rows which are very faded, and these would correspond, of course, to the to misdiagnosed patients. There are patients who have MDD, they have been told that they do not have. But most of them, as you see, is a really colorful one, meaning that the amount of differential entropy is really high. That quantifies the amount of activation. Okay, Cecile, I think that gives a pretty much good overview of the method and the results.
Yeah, I just want to ask you, you said earlier that there might be a recorded seminar that you presented at the Phillips Institute. That
I couldn't actually make it. I couldn't actually make it to I had to cancel that. I had to cancel the seminar. So it was the last minute decision. Anyways, I couldn't make it there. But I believe the one that we have here, since we discussed on the paper, it should be, to some extent, should be I mean, if you believe there's anything else that we can do to just help improve the quality of this presentation, I'm totally open to that.
Yeah, I think we had a great discussion here. It's just that maybe the app is, of course, basically just audio. So there are limitations as to what we can really make in the presentation. But we will post the paper that you have. There were people who weren't able to make it this time because of the time zone. But probably in the future, we can bring that up again because, even in my other social media that I posted about your work, there were they are not in Clubhouse, but there is a lot of interest that was being expressed about the potential future applications, and not only now. And as I listen to your conversations, even with Serena and Hansen, I don't know what will happen in the future, but I could just imagine and would like to, if experiment on potential applications of the Lemur transform. For example, in music, like there has been not much study about microtones, and that is a very interesting field maybe to go into in the future. And like you say about the financial and about the health, and particularly on the presentation that you made with the paper, it's really very, very interesting. So yeah, maybe in future rooms, if people would have more chances to read your paper, because this club is has a lot of audience also among the neuroscience professionals and enthusiasts. So maybe if they read the paper closely, they can ask you more questions. So let's see what we can do to bring the topic back again in the future. And with this, I would also like to extend an open invitation to you in the future, to talk about other topics. And last time when we talked about Ramanujan, I know that you wanted to talk about, a book that tried to dissect the concepts of Ramanujan, and probably we can also have that room in the future. But as regards this paper and the study that you have, maybe we would like to bring further conversations in the future. Let's see what we can do. So we are here for almost 4 hours now, and we would like to really thank you for your time and for your expertise, Dr. Masoud. We really learned a lot from here. Yeah,
that's my pleasure, and I would be more than glad to actually to get more feedback on this on these results, because that's actually something which I believe can help me improve and understand this transformation in a better way. So, because I've proposed the transformation doesn't mean that I have a full understanding of that. So, I really look forward for very constructive comments that the audience can provide, and obviously different applications, like a wide spectrum of applications. I never thought about the applications in music, but now when Serena actually mentioned that was quite new to me, because I never thought about it, and it's very interesting. There's several aspects that I can see that definitely related, but how it needs more investigation. I'm pretty sure there's so many other problems that from different areas. Each one of us, they have like certain capabilities. Like for the financial ones, I would say to some extent I have the domain knowledge to a great extent, but the neuroscience or the psychiatric results, I would really I'm looking forward to have some constructive feedback, which eventually I'm pretty sure is going to help this transform get more mature, so that it can actually tackle more complicated problems and give us interpretable results, tangible results, rather than results that are kind of a black box and we don't know how they work. So this was initially, from beginning, my approach to develop something that is easily interpretable, and I hope I've done that task. I've done my best, but I don't know how good it is right now. But I'm pretty sure any feedback can actually help improve this method, the entire framework. And I'm always, this is a pleasure. It's a pleasure to be here, and for sure, for the future discussions, you can count on me. Yeah. Thank you for holding, and thank you for all the audience for being here for more than 4 hours, I guess. that's a long.
Yeah, for something which is like very technical, and not all of our audience really are into this field deeply, but we have people who listened up to the end of the room. So I see Bob there down. He is the one editing what we have recorded to YouTube. So maybe if he has edited some version of what you have now, we can give you a copy in the future. And
that would be great. Yeah, thank you.
And also, Dr. Masoud, maybe what we can do in the future, we will let people, for instance, people in neuroscience or in neuropsychiatry, before we have a room, I will request several people to read the paper, and maybe we can have just like a focus group or a panel to discuss their questions with you, or even people in data science, or math.
Yeah, that would certainly be very, very effective. That would be very, very effective and efficient to really get into the details, to the those subtle points, and discuss those ones, either from the mathematical perspective, but also I'm looking really forward to get comments and feedback on the application side, because the theory is one part, but how it's applied to the practical problems, and that requires domain knowledge, and acquiring a domain knowledge in any domain, that would take time. That would take 7 years at least, maybe 9 years, 10 years for psychiatry. Yeah. Dalso, hello.
Yeah. Darcel. So anyway, Dr. Masoud, we are just about to wrap up. Thank you for spending time with us, and we look forward to having you back here. Anytime. Actually, I would like you to, if it were up to me, I would like you to maybe have a room with us every once in a while, maybe even once a month, about certain topics, because I know that you have other areas of expertise. Maybe talk about in AI in general, perhaps, or maybe try to talk about lemma or something. So, or even just math history. Yeah, I would very much like to invite.
That would be my pleasure. My pleasure. Yeah.
Yeah, so I'll just talk to you at the back channel. I really, really appreciate your presentation here today. And we have Rishi also here. Thank you for asking interesting questions. And we would like to close the room soon. I would like to announce the next room. We're going to have a postdoc scientist from NASA who's going to talk to us about the origins and destiny of the universe. Of course, it's going to go to the basic concepts like the Big Bang and the dark matter, and black holes. So, in less than 24 hours from now, we will have a room on that. So please watch out and please follow Quantum Photonics. So, with that, we have Darcel here, who is our timekeeper, who stayed with us very patiently today. And, Masoud, Darcel is also into music. And I would just like to say that what discussions you had earlier also awakened something in me about, thinking about the applications of the Lemur transform. As I said, in many cultures, in what we traditionally know, we know only limited notes, but we have not understood or explored other notes. That's why I was talking about microtones, because in microtones, we will realize other notes that we have never been conditioned or we have not yet imagined, because, these are the only things that were taught limitedly to us. So anyway,
That sounds like a very promising area to me, and I'm getting to just see the point here, actually. When Serena mentioned it, I didn't quite understand, but I can see that those countable number of nodes, what if we just consider the spectrum, perhaps it's gonna generate something, something definitely new, but how that would require, I would say, people with the domain knowledge like yourself or Darcel or Serena to really work on these, help like somebody who is working with the transform to provide them with the all the information, because it's not possible for a person who's only working with the nodes without understanding the theory behind the music to just develop something. So it is really sometimes a teamwork, and most of the time one needs to just acquire those mathematical skills, the one having the domain knowledge, and just apply them. And I believe that's the most promising path. At least that's the fastest. That's the fastest one, which can yield promising results. Yeah. With this, I would like to say goodbye to all audience, and hopefully, next time we will continue the discussion.
Yeah, very much looking forward to that, Dr. Masoud. So now, I would like to say good night. We are here with Darcel to start the countdown to close the room.
Thank you, Cecile, for bringing me up, and thank you, Doctor, for an excellent room. And before I start the countdown, there's one thing that I would like to request that when you come back that you kind of talk about, and that's the non-stationary spatio-temporal time series. The analyses, and I guess it's econometrics and econophysics regarding to what Cecile said about the microtones and how that all plays together, and how that plays in the world of the quanta. I'd like to hear more on that, on your thoughts on that, if that's okay. And then I'll start the countdown if that's okay.
For sure. I do actually have results on the higher dimensions and basically embedded within tensors. So it is actually, yes, for sure. That's a very good point that you mentioned, and that is one of the focal points within my research. So yeah, next time I will actually present some of those results. Hopefully it will help. Yeah.
Great. All right. So here we go. We're going to start with lucky number 5, everybody. Are you ready?
Ready.
5. 4.
4.
Help us out, Doctor. 3.
3. 2.
Doctor, you are number 1. Call out the last number.
1.
Yeah.
Yes. So thank you so much, and good night, everyone. Yeah, see you again soon. Yeah. Au revoir.
Have good dreams, everyone. Thank you.
Okay. Goodbye.